bit. I should mention this meeting. This meeting is going to be recorded, indeed. And we are going to have this afternoon a symposium on theory and methods for energy materials. We are still waiting for our guest speaker, Professor Peter Littlewood, and we'll just wait a few more.
Peter's arrived, Cedric.
Oh, hi, Peter. Good afternoon.
Good afternoon.
You might be able to share your screen, Peter. I think if it all works fine.
Okay, do you want me to do that now?
Yes, and then I'll start to do a short introduction, and then I think we can get started. While Peter is sharing his screen, so I think Peter hardly needs any introduction at this stage. I might just remind everyone that Peter has been in leading position in many institutes, in particular at Bell Labs, before he moved to the Cavendish Laboratory, and then was the director of the Argonne National Laboratory, before now being based at the University of Chicago, with many and different influential position. One of them particularly relevant for this meeting, which is Faraday Foundation. So Peter, anytime you are ready, we can slowly get started.
Great, no, thank you everybody. It's very kind of you to invite me to speak at this. I'm delighted to see the kind of effort which is now going in the UK actually to materials modeling for energy materials. And so, but I'm actually going to use this opportunity to just talk about some of my own recent research, which is actually collaboration with a former student in Cambridge, Richard Briley, and a former postdoc at Argonne, Jan Guzman Very, and some of you will know both of them actually, because they've spent, obviously Richard, but also Jan has spent some considerable time in Cambridge. And I want to talk about an odd and under-investigated area of materials design, which is actually making use of elasticity. And unlike many of the other talks, which will, I think, have very sophisticated numerical methods, this one is kind of old-fashioned, although I think the style could be reinvented in a modern world, because of what I'm really doing actually is data mining and trying to understand what comes next. So let me just now remind you, actually, I'm going to be talking about transition metal oxides, very largely perovskites. But these are buried in vast amounts of stuff. And in particular, they're actually in things like small devices like ferroelectric memory. Famously, transition metal oxides are the battery cathode of choice. They're used in electrocatalysis and fuel cells, materials with magnetoresistance. Favorite of mine actually is electrocaloric materials for refrigeration. And the reason that they're so widespread is that the properties are so variable. One can make from these things ferroelectrics, materials that conduct ions, ferromagnets, metals, insulators, and they have a wide variety, and of course superconductors, and they have a wide variety of behaviors. And one of the goals of designing materials in this space is to be able to tune their properties by chemistry or by other means, and I want to talk about that. And specifically, I want to talk about how you can tune something which is very fundamental to this class of materials, which is what I call the Mott transition. So I'm sure many of you will have seen this model. It's a simple idea, of course, which is to say that if I have Coulomb repulsion between carriers in a solid that is competing with the kinetic energy associated with electronic hopping, there is some boundary associated with the ratio really of the Coulomb interactions to the kinetic energy, where I cross from an insulator to a metal. That often happens as a function of temperature, can happen as a function of parameters. And of course, while my paradigm for this is the Hubbard model, actually there are vast numbers of broken symmetries that occur in all of these materials involving the spin, spin-orbit coupling, the lattice, the charge density, etc. Now, there's a central dogma really in the theory community that, that the important parameters are just all electronic. As I said, really the ratio of the interaction to the bandwidth, and then probably the number of carriers in the band, and that while one sees, of course, coupling to the lattice, it's mostly irrelevant, or it simply renormalizes the parameters. And one should work with entirely electronic models. The first thing you should see about that, you should worry about that, is you say if the energy scales are all electronic, why isn't the transition temperature typically volts? Transition temperatures for all of these materials are actually typically hundreds of Kelvin, much smaller energy scale. And so if the electronic problem is likely to give you an energy scale of order volts, you need to find some entropy that lowers the transition temperature from electronic energy scales. And I'll point out here that all of these Mott transitions couple to lattice degrees of freedom, to elastic degrees of freedom, and I want to talk about that physics. But as an example of the phenomena, here's an old plot, actually, from more than 20 years ago now, 30 years ago, actually, of along this axis is the first d orbital count in transition metals. Again, all just for perovskites here. So, and plotted along this axis is this nominal parameter, which is U over W. So strong Coulomb interactions up here, weak down here. And this grayed out area is the boundary between an insulator and a metal. So we're often used to thinking about metal insulator transitions, which are produced by doping. And so that involves going from something here, moving across. For example, in this series lanthanum calcium manganese oxide, you start with an insulator and then you become metallic at some point. But it's worth noticing that you can also go vertically on this axis. So I can work at constant chemistry. I'm not changing any doping in the material. And I can just change, in fact, ionic sizes. And by changing ionic sizes, I can, actually in every case, cross from a metal to an insulator in this series, without changing chemistry. And that's in many cases, it's a much more dominant behavior than the actual case of doping. Let me give you an example of how this works, because I'll be talking about manganites a lot, of the perovskite manganites. And so this here is the perovskite structure. There's a manganese sitting in the center, the green atom. It's surrounded by an octahedral cage of oxygens, which connect to the next unit cell. And then at the corners of the cube here, there are either rare earths or alkaline earths, which are providing the reservoir of carriers that move into these layers. A bit of chemistry about this. In a cubic environment, manganese, the D levels would split into a triplet and a doublet. And manganese 4+, which would be the end if I had complete calcium doping, would simply have the 3 lowest levels filled. Hünzrühl will line them up. There'll be a strong magnetic moment. If I go to manganese 3+, so that's at the lanthanum end of this, then there's an electron which is promoted into the EG level up here. And this will normally, of course, want to hop around and try and make a metal. As it does so, as it hops from site to site, it finds it easier to hop, of course, if this is aligned with the spin. of the core, and therefore the kinetic energy, the hopping, promotes ferromagnetism. But there's another thing that can happen, and the other thing that can happen is a Untitled distortion, because if this is completely cubic, indeed, these two levels are degenerate. If I make a distortion where, for example, 2 of the oxygen atoms move in and 2 move out, I produce a gap here that localizes, that splits these levels and localizes this carrier. It reduces the hopping, and actually it drives you to an insulating state, typically which has orbital or charge order. So this is one of the many examples of what I'm calling Mott-like transitions, because Coulomb correlations are enormously important in why this happens. But equally, the coupling to the lattice matters. So here's some data on that system. Again, this is very old. This is a pretty old topic. Actually, it goes back to Goodenough in the 1950s, rediscovered in the 1990s. Here you see the resistivity, log scale, as a function of temperature for this series, lanthanum, strontium, manganese oxide. At x equals 0, lanthanum manganese oxide is actually is an insulator, quite a robust insulator. As you dope it, however, you begin to see a kink appearing here at this, where there's a transition from something which is a very bad metal at high temperatures to something which becomes quite a good metal at low temperatures. And this is the onset of ferromagnetism. That's the transition I was describing. Up here, one has some kind of soup of localized, quasi-localized carriers. But down here, those distortions vanish, actually, and you have a good metal. Now, it seems natural, of course, that as I dope with carriers, I move TC. But what is less obvious is that if I work with exactly the same carrier density, so this is 30% doping, but I simply change the size of the ions by doing things like replacing strontium by barium or lanthanum by praseodymium, I can produce a phase diagram which now looks like this. And you see that by changing what's called the tolerance factor, but it's just basically the ionic radius of the A side cation, I can change the transition temperature by several hundred degrees. There's no obvious chemical changes happening here. This is all structural. This is the same data here, and this was analyzed in detail, actually, by Paul Hatfield and a student, Rodriguez Martinez, a number of years ago, where they really quantified this and extracted effects which are both to do with systematic size effects and also disorder. I'll talk about both of those later. But this is their data. This is all data. The only thing which is being changed here is the ionic radius, and TC goes from 0 to 600 Kelvin or so, and fits rather well to some parabolic form. So let me remind you, that's just one example running up here on this axis, and there are many others. Most of them don't have anywhere near so much systematic data. So why does that happen? Well, firstly, what happens when you change the ionic size is the octahedra rotate. I drew the perovskite structure as if it was perfectly cubic. That's very rarely the case because there's some ion which sits in the middle here at the gap in between these octahedra. If it's a small ion, the system tends to buckle. And if it's a large ion, it tends to push out and become straighter. And so, of course, that changes the bandwidth of hopping from one manganese orbital to another manganese orbital because it has to go via an oxygen, and there's basically a cosine theta, cosine phi dependence of this hopping matrix element. So the bandwidth is indeed changed. So if you have very small ions, small radius, then you expect to have a smaller bandwidth. And that has always been one view of why the phase transition could be tuned by size. Namely that the Coulomb physics was the same, but the bandwidth was changing. So here is, of course, a plot of that versus, in this case, versus the estimated bandwidth from Paul Radiali. And in this case, different system, nickelates. Again, the transition comes from several hundred degrees down to 0. Lanthanum doesn't transform as a function of cosine phi. But I'd just like to point out that these changes in angle are quite small. And the implied changes in bandwidth are a couple of %. And it seems odd then that with a few % change, one can always move in all of these systems up and down on this axis, that you're sort of tilted perilously close all of the time to this phase boundary. So is that really the answer? I'm going to suggest not. Let's see, what time have I got? I may run quickly through this. I'm not going to talk about this. I think we don't really have time. So here's a cartoon of an idea. What we know is in this transition, again, specific material, lanthanum, strontium, manganese, I go from a ferromagnetic metal, and in the ferromagnetic metal, my cartoon of the ordered phase is that all of the manganese are the same. They're all basically cubic. There are no Untitled distortions. And I would sort of paint this in a two-dimensional map to look like this. So these are the manganese. These corners here are where the oxygens join. However, if I'm going to go into some disordered or perhaps ordered phase, where I have Untitled distortions, the octahedron has to change shape. I've, again, put this in as some kind of diamond-like shape. And I have to get a configuration which looks rather like this. So there's a constraint, of course, and the constraint is that every octahedron is connected at the corners. So I can't arbitrarily vary the shape of neighboring unit cells because there is a constraint on them all packing together without the crystal falling apart. So then the question becomes, if I want to make that disordered phase, how do I do it? Here's a little bit more detail underneath that. As I say, manganese 3+ likes to be shaped like this. Manganese 4+ likes to be like this. And the problem is, if I want to have a mixture of these things, which is disordered, I have a mechanical problem of joining things together. Equally, if I want to make a transition from a phase which is uniform like this, and one which is Jahn-Teller ordered like that, you notice that if I just change shape of these things, there's a mechanical force that requires essentially every unit cell to behave the same. If, however, I also allow the octahedra to rotate, I allow inhomogeneous patterns. And I'll be more specific about that at the moment. So in a situation like this, where the octahedra are free to rotate, I can actually make much more complex patterns at lower energies and therefore explore the entropy associated with these phases at a finite temperature. So let me turn this now into a toy problem before I turn it into a real problem. So I'd like to argue that the model you should be thinking about is a model which has really 2 degrees of freedom that I care about. A Jahn-Teller order parameter here, which you see is naturally staggered. It goes plus on one side, minus on another side. And U is just the magnitude of this distortion. And then there's a bond angle associated with oxygen. And it's very tempting then to write down a phenomenological free energy that would look like this. So there's 2 components. One I've just pulled out thinking of U as an order parameter. So this is just a Ginzburg-Landau theory for this. I've got a quadratic, a quartic coefficient, and a gradient term, which is the cost of making variations in the displacement. So normally one would, of course, say that there's some temperature where alpha changes sign, and below that temperature, I would in fact expect this to disorder. Sorry, to order in this in this pattern, and above that, I'd expect some possibly disordered phase. And then I've added, just arbitrarily, some elastic constant for bending this bond relative to the equilibrium rotation. So there's an equilibrium rotation, and then there's fluctuations about this. So I'll propose that as a free energy. Now, that's actually not really very encouraging, because I've written down a free energy with 2 degrees of freedom, but I haven't coupled them. And I should now explain why they get coupled. And the reason they get coupled is via what's called compatibility relations for strain. So if I think of the volume strain, so basically just a change in volume, which I'll call phi in here, as just this two-dimensional model. One way of changing the volume, of course, would be to change this angle uniformly everywhere. The volume change goes roughly like the square of the angle. Actually, it's cosine theta, but for small angles, it's quadratic in this. And then the other way I can change the volume is if this variable u actually has a gradient in it. So if this changes, if there's a gradient grad u, then that also produces a volume, because I can make this get smaller. So that produces volume strain. In order for strains to be continuous, I need to satisfy what's called the elastic compatibility condition, which is a generalized Poisson relation on the strain. I've ignored the other 2 components of the strain. There's some additional terms if I have shear in, which I'm just, for purposes of illustration, neglecting. I actually have to satisfy this. If you don't satisfy this, your crystal cracks. So notice that that's a constraint in how the gradients of the order parameter can vary, associated with spatial variations of the angle. Let me simplify that a little bit by linearizing in theta around theta 0. And after I've linearized, then fluctuations in theta about theta 0 go with gradients in here. And therefore, I can take this term and replace it with the square of that term, which of course then looks like grad u squared. But notice that there's a theta 0 squared in the denominator. And so that tells me that my stiffness gamma is enhanced by a factor of kappa over 2 theta 0 squared. And in this very simple model, you see that the system becomes infinitely stiff as theta 0 goes to 0. And so that's the physics that I was trying to describe before, that as you remove the ability of spatial fluctuations to be screened by rotations, then you get this stiff. And by the way, this is just like the stiffness of an Euler strut. If you take an old-fashioned meter rule and push on it from the end, it's very stiff until it bends, and then it becomes softer. This gets into a little bit more microscopics about this, but this microscopics is all geometry. So what we did for particular models is we decomposed this elastic interaction into local modes. So if I think about an octahedron and how it can change shape, here, for example, is the Antella mode. I call it T. This one uniformly changed is of course corresponds to volume changes. Here are the rotation degrees of freedom, and here is the other kind of shear, all done in 2D. These 4 local modes overdetermine the positions of the oxygens, so they're not independent, and you have to decide which one of these you want to focus on. So for example, for manganese, it's this one. For the nickelates, which actually have a volume changing transition, it's really this one. And effectively what you do is we start with a model which has got simply purely quadratic elastic theories, plus some nonlinear local terms that I'll talk about later. Remove the effects of overcounting, and then optimize to get an effective interaction. And what does one get? Let me just focus on this. So here now, this is, so K is wave vector, L is the size of the unit cell. And so this is just a tangent, but at small k, these are just k's. So, so here's the interaction you started with. Here's the one that is generated, call it V of k, by integrating out the other degrees of freedom. It's got some complicated pieces, but it's not too bad to get. The main thing you might notice is that there are powers of k, which are of order k fourth in the numerator, and there are powers of k of order k fourth in the denominator. In certain directions, as k goes to 0, this vanishes, and in certain directions, it's constant. So this is a very long range anisotropic interaction. And moreover, it's modulated by the Baire angles. What can we do next? So this is what it looks like. So if I make a little model and I insist that I'm going to put a yarn telepolaron at the center and I'll let everything else relax, so I'm just pulling this by hand, you see that what it does is it generates what are effectively a domain wall pattern. If the system is allowed to rotate, then these long-range interactions are still there, but you see that they're considerably softened, actually. There's a lot more fluctuations allowed in the neighborhood. Okay, and if you like, look at that behavior of those, of that plotted as a function of angle. This is the anisotropic elastic interaction. And again, done for two different cases, for manganites and nickelates. And notice that, again, the symmetry is different. This is, in this case, this is aligned along one axis, and this is aligned on the other, and that's because of the form of the unit cell. Okay. So how do you turn that into a theory? Well, you can calculate things. Well, that's a quadratic interaction, which is long range. I will assume or infer that there is some local theory which would describe the actual strong correlation physics of the problem, which is really all on one side. So here is my Landau theory, but I've written this in real space, and this is nonlinear, but it's entirely local. Sorry about the mumbo jumbo here. This is just a statement that we're going to solve this at the level of a mean field theory, which one can do. And I'll now show you what comes out of that. Well, I should say something about parameters here, actually. Essentially, all of these parameters are here unknown because they can really be extracted from elasticity theory. So there aren't parameters there. There are several parameters here, but effectively these are really determined by a fit to one piece of data. And H, by the way, are random fields, and so that's another variable. But actually, you really have only sort of two unknown parameters which you have to fit. So this is what one gets with that. The very simple model from a transition from a ferromagnetic metal to polaronic liquid. The red data points are the data from Paul Attfield's lab. And furthermore, Paul also noted that disorder in the A site radius has as much of an effect as the average radius change. And you can understand intuitively why that is, because if you've got big ions and small ions, it's easy to line yourself up along with the distortions in the places where they fit, actually. a few other things in the model, at least. There is actually some point where there's in somebody's language, a quantum critical point, but this is all phonons. By the way, there are materials you can find which sort of sit here. My favorite is actually Scandium Trifluoride. It's a lovely material that manages to maintain cubic despite not having an A ion. But you go from this to this. We also applied that to nickelates, where again we've got a lot of data. At low temperatures, there is an anti-ferromagnetic transition in the nickelates, so we don't really have anything to say about that. But my own view is that it's typically the insulating phase transition is robust, and typically the magnetic order takes place at a much lower temperature. I just want to close with a few remarks. No, I mean, it's sort of an odd thing to be doing, if you like, electronic structure theory this way, without doing any electronic structure at all. But I'll point out that doing the statistical physics of long-range interactions is not something which is easy to do, combined with ab initio methods. So it's very hard to do ab initio calculations at a finite temperature on the system sizes that you need to describe that. So there's all kinds of good reasons to want to be able to, excuse me, take your best ab initio methods and then combine them with something which incorporates this kind of longer range physics. And so that's something we're beginning to do, because one can make pretty good ab initio calculations using, say, dynamical mean field theory, which are quite good to get the local energetics of these metal-insulator transitions. So this is something that we're beginning to do in collaboration with Hyowon Park, who's at UIC and Argonne. There are actually some technical challenges about how to separate the terms, how you get them out of an ab initio calculation. I'm sure many of you will understand this. A small theory point, because we have long-range coupling here, it's actually quite possible that they can really be a true glass. So coming back over here, actually, the data down here looks often like a liquid to glass transition as one comes through here. That's not captured by the kind of theory that we did. We have, if you like, a replica symmetric theory. To get true glasses, actually, one needs a long-range coupling. But we indeed have that, and so it's interesting to know whether it's going. I believe, although I can't prove to you, that this is likely to be operative physics across the whole of the transition metal oxide series, and probably including non-perovskites as well. As I showed you, the old figure from Fujimori suggests that one can tune these transitions with atomic sizes. And on the basis of that, I think this may be an underappreciated direction for materials design. If you want to make an electrocaloric material that has a transition around room temperature and has a large entropy and latent heat, you actually want to be able to manipulate this physics to tune the behavior in that place. If you want to make a soft and floppy structure where it's easy for cations to migrate from site to site inside the structure, as you might need inside a battery electrolyte material, solid electrolyte. Again, this is something that you should explore, that one might explore. and with many other things that one can do this. And then my last point is that the only reason I got to do this was that Paul Hatfield posed this problem by recognizing that the data was there, the systematics. I mean, there's initial work from Harold Huang who pointed it out, but Paul systematized this. So I had a database where I could discover that there was a trend and think about ways in which I could fit it. Actually, nowadays one would probably begin that process either by data mining from the literature or actually by data mining from ab initio methods. It's now, as we'll hear later today, quite easy to collect large amounts of ab initio data that inform you about trends. But then I would say the point of that is then to use it, to harvest it, to build models which are simple enough that they can really generalize. And that's what machine learning is supposed to do. And I think with that, I've ended roughly on time. And I'll stop sharing.
Actually, Peter, you still had 15 minutes. So if you want to make use of them, by all means, feel free to do so. Or otherwise,
okay.
We'll just extend the discussion.
It's okay, sorry, I misread my calendar. Well, in that case, what I will do is I will go back to show you something else, which I rushed over, and make a point which is perhaps clearer. Because that will go, so I need to go back to screen share. Where is Zoom? So let me go here. Because I want to point out that this, I didn't want that, I wanted this. So I wanted to point out that actually this phenomenon on microscopic scale is well known actually on long scales. And so, and to connect it, therefore, with something which is in fact well understood to metallurgists. Although I won't do it with a metal, I'll do it with a ferroelectric. Let me think of a material, say like barium titanate, which at high temperatures is cubic, and at low temperatures acquires a dipole, a macroscopic dipole that points in actually one of 6 directions, broken symmetry. And because the dipole points in a particular direction, like this, let me just get my pointer again. So because it points in one of these directions, the crystal changes shape. This is a macroscopic version of what I talked before. Okay. And so that means that domain structure in ferroelectrics is very strongly constrained. So if I have a piece of material which transforms, I typically get just 2 kinds of domain wall really allowed in the system. One is so-called 180 degrees that looks like this, with an anti-parallel, and the other one is a so-called 90-degree domain wall. And the thing that makes these things stable is that they have no polarization charge and no elastic stress. It makes them very difficult to bend. And just as a homework exercise, you can ask yourself, what is the dynamics of a domain wall? Say a 90-degree domain wall here, which I've now rotated, coming like this, and here's the line where it goes. And you can ask yourself, homework question, which is if I make a wave on this, after all, it's a very long wavelength. That's sort of the natural mode of a surface, like a water wave. As the wavelength becomes very large, or as the momentum k goes to 0, you expect a dispersion curve. I'll call it the restoring force as a function of frequency, as a function of momentum, omega of k. And because there is translational invariance, you would expect this curve to produce an acoustic mode, or at least a mode whose frequency vanishes as the wavelength goes to infinity. So a slightly longer version, and extending a little bit what I just said about elastic compatibility, one can do a 2D elastic theory from this from Ginsburg-Landau, and this is very well established in materials like barium titanate. So here, the polarization is the order parameter. Here are, in this case, 3 components of strain, and here's a coupling of px squared minus py squared with the component of strain, which is the change in shape, one of the components of shear. So it's this coupling term that produces this shape change. When I produce a polarization in a particular direction, the crystal deforms to accommodate that. Here's actually the generalization of of the elastic compatibility condition with volume strain and 2 kinds of shears. This is required for your material to be behaved, because of course the strain components overcounting. You've generated 3 in this 2-dimensional theory. You've generated 3 2-dimensional fields, but you only needed 2 to describe the position of the atom. So one of these are redundant. If you do that, I can, of course, eliminate the strain, as I did with the microscopics, and get a coupling then between the polarizations. Because here strain couples to polarization squared, that actually generates a p to the 4th term here. So this is the new generated term. These are the original ones. Which is not easy to write in real space, so I've written it again in Fourier space. So gamma of k squared is just the Fourier, gamma of k is the Fourier transform of the p squareds. And h of k is the kernel. And here I've kept dynamics. So omega is frequency and k is momentum. But you notice, as before, there are as many powers of momentum in the numerator as there are in the denominator. And this produces an infinite range, but actually in this case, retarded and strain-mediated coupling. That has some interesting consequences, particularly the fact that it's retarded. Turns out if you work out that mode dispersion, and we'll do it in a case where, if you like, the velocity of sound is infinite, then you get a dispersion curve omega of k, which is actually a square root. That square root comes both from the dipolar forces and from the long-range strain. But particularly from the long-range strain, you notice that this has this tsunami-like dispersion, so the group velocity gets larger and larger as k gets longer. But of course, some of this is then exceeds the speed of sound. So the actual dispersion of the mode has some finite sound velocity, and therefore all of the modes here are trying to propagate faster than the velocity of sound, and they can't do that. And consequently, the retarded response produces a gap. So you cannot propagate, at least without some extra physics going on, these modes at very long wavelength, because at very long wavelength they produce bending. The bending transmits forces over long distances by the strain field, and those have to be carried at the speed of sound. This is statically well known. It's called strain clamping in ferroelectrics, and it corresponds to a shift in TC, depending on whether you've got a thin film which is clamped to a substrate or a solid which is free to change shape. So that was perhaps supposed to be an introduction rather than a conclusion to this. But the point about this is that this is relatively well understood physics at long length scales. People who worry about the formation of so-called tweeds in materials are kind of well aware of this dynamics. Of these elastic forces, but actually it has dynamical consequences as well. This, for example, is one of the things that controls the rate at which it's possible to switch a ferroelectric device, because it's not impossible, but it's very hard to switch them faster than the speed of sound. So then I really will end. I think that's a good point, and see if there are some questions.
Brilliant. When you have a question, if you may just raise your hand so we can take questions in order. Feel free also to type your questions in the chat. Alternatively. In the meanwhile, I had a short question, Peter. You mentioned indeed quantum criticality as a function of the size of the ion. Usually around quantum critical point, we get large fluctuations, and I was wondering how you think fluctuations might enter into your theory.
Yeah, I mean, I think one will. So there are a few systems where I think one can study that, and we're wondering about it. So there's the famous old chestnut of strontium titanate. So strontium titanate is very nearly ferroelectric. It has a dielectric constant of about 20,000. And there is in that system evidence for very strong fluctuations, which has been put forward by the Cambridge group. How you treat them, I'm not sure. My favorite material, so at the moment, is I might just be able to find it if I look quickly. Is a material called scandium trifluoride. And I think I have one slide on it somewhere. Whoops. Which one was speedier with this? Voice controls. So here's a quantum critical problem, which is interesting. Scandium trifluoride, it's a perovskite structure. It has no A ion. It's electronically a vegetable. It has a gap of about 5 volts. But remarkably, since even though there's nothing in the middle here, and you might think that the system would kind of fold up in these different structures, it doesn't. So scandium trifluoride actually, it stays cubic all of the way down to 0. Despite the fact, and here are the fluctuations that you were talking about, if I look out on the zone boundary, there are soft zone boundary modes running all of the way from the N to the R point in the Brillouin zone, correspond to these fluctuating rocking motions. And they're incredibly soft. They soften a lot as you go down to low temperature. This, by the way, makes this material a well-known negative thermal expansion. Because as you raise the temperature, the fluctuations get bigger and everything comes in together. So this is something that Martin Dove is a specialist at, actually. But notably, here's a quantum critical point, and notably, here I'm changing the radius of the earth ion either by doping scandium with yttrium or with aluminium or with titanium. And the moment that you add something to it, it orders. So this is actually an indication, to my mind, of very strong, let me call them 0-point fluctuations associated with these phonons. And we understand that the system doesn't order here because it doesn't know whether to order at M or at R, because this dispersion curve is essentially flat. So there are so many fluctuations along this line that it can't find a place to order to until you give it some disorder. And the disorder, because of nonlinear couplings, then is going to favor one or other of these points, and actually favors the rhombohedral one. And then it orders. So this is, I think, an example of what you might call order by disorder phenomenon, which is famous for various kinds of magnets, but really demonstrates, I think, that there are very strong fluctuations available in tuned systems that are close to a critical point. So a long answer to your question, but this is, I think, a really very interesting model system to understand.
Brilliant.
And by the way, the other place one sees that in materials we're more familiar with is lanthanum nickelate. Lanthanum nickelate stays metallic down to very low temperatures. It's at the very end member of that series. And it has very strong fluctuations that you can see in susceptibility and resistivity, which have been ascribed to magnetism, in my view, I think wrongly. I don't think those are magnetic fluctuations. I think those are lattice fluctuations to it.
I think Sarah had a question as well.
Yes, that was a very nice way of bringing together that interdependence between electronic structure and the motions of the atoms within the solid. But my question is that both sets of theories tend to invoke an infinite periodic lattice. How important on the properties that you're actually comparing with as measured are the existence of defects, surfaces, the small size of the particles?
I think very. I mean, I agree with you entirely. So I mean, as I noted, even when we treat disorder at the lowest level, we miss a lot in terms of glassy structures which are there. And there's also what you might be able to do with nanoparticles by actually using them to relieve these strain effects. So I think that's absolutely critical, particularly if you want to do something practical to design materials that will be useful under certain applications. These are bits of tools. But what I will also say is that, if you make the kind of model that I have got, if it's well enough parameterized, one can simulate that. Those models are very easy to simulate with molecular dynamics to put in those kinds of effects to see how well one could tune through that. So at least so the idea would be to do the best ab initio you can at the very microscopic level, to then incorporate that into sort of the next level of modeling, but in a way that you can then put this to it. And of course, that's been a long goal for these things. And the bit that I'm adding is to point out how long range some of these interactions can be and how constrained they can be. But that then makes the effects that you're talking about even more critical, because I can adjust this by changing the shape of the objects I'm working with, the kind of defects I put in. It's where the defects find themselves. I mean, defects migrate in strain fields to get to the places where they're of lowest energy. And then all of those things can be effective, even in terms of, then the functional activity of whatever you're putting the defect in. So I think these are things that we really need to pay a lot of attention to.
Thank you.
We have time for a last question, and excuse me for my pronunciation, Charles.
Well, thank you for the lecture. I think my question is more naive. That's actually I'm trying to understand this theory that's in two aspects. For one thing is, can I imagine this theory is to find some baseline of the critical temperature and tune this temperature by some micro perturbation of some volume and other stuff, that I can find the variation of the critical temperature based on certain parameters? Or can I actually connect, let's say, different components or different phases of the materials, and then using this this theory to predict actually, materials with same chemical component, they have different phases. That if I can use this theory to connect materials with different phases, still I can predict the correct, let's say, transition temperature or other physical properties of the material. Thank you.
No, thanks. Actually, not a naive question at all. So, of course, so the first thing is you will understand that this theory isn't an entirely practical theory at the moment. What we really did was to understand the phenomenon. How is it that you can tune a phase transition temperature as measured by such a lot with what is apparently a relatively small perturbation? So the goal was just to understand that in principle. And a few other things come out. I mean, you notice that the phase boundaries tilt in different directions. You do things like predicting out of this the pressure dependence of TC and this. But it's too simple to be useful in the way that your second question is. But that really is the goal. In principle, to be able to build models where I either have parameterized local free energies or calculated local free energies, and then I can find potentially new states. So here in this theory, I only compared completely ordered and completely disordered states. I didn't look for striped phases, which certainly exist at low temperatures. And I'm sure the model has in them because it's got all of these, as you saw, strong anisotropies in there. So it's not being explored in any great detail, nor is it, I think, functional yet at a level of something where you could do it to explore, I think, a new piece of phase space. But that I think is then the goal. I hope that's a decent answer to what you said.
Thank you.
So I think this is a good opportunity to thank Peter very much for his talk.
Thank you.
I don't know how we can do that on Skype, but let's all applaud Peter. Thank you.
Thank
Peter.
You very much. It's a pleasure thank you for inviting me, and I'm looking forward to the other talks.
I suggest that wait 2 minutes for everyone to stretch his legs, maybe do a coffee, a cup of tea, and we'll continue with Professor Chris Pickard and his talk entitled Random Search, a Tool to Explore Energy Materials. So let's reconvene in a couple of minutes at 58.
Hi, Cedric.
Hi, Chris.
So should I just, I'll share my screen just so that it's there.
Yeah, indeed. Yeah. If you can manage.
Okay, not quite sure. Has anything happened? Yeah.
Yes, I can see your screen. It should be fine now.
I was going to try and put it in presenter mode so it's possible. Okay. I don't think that quite works, does it?
I think we can see on next slide as well.
Yeah, I was trying to make it smooth. I think that may not be possible through Zoom.
Are you using Microsoft, isn't it?
I'm using Keynote, but...
Oh, then you have an option to play in a window instead of
okay, let's try that.
And that works quite well usually.
Okay.
So if you have
play Shiso in a window.
let me have a look.
Have you got it now? Ah, it's paused. Okay, what's happening? Can you? Let's try. I'll try sharing again. You got it now?
Yes. Yeah. Now we get it. Yeah. Yeah. Fantastic. So I think, Chris, you can, whenever you're ready, slowly get started.
Okay, I'll slowly get started. Okay, so hello everyone, wherever you may be. It's always a pleasure to come back to the TYC and talk to people, talk to my old colleagues there. And thank you, Cedric, for inviting me to talk in this, this symposium. So yes, I think Peter has sort of anticipated what we're going to hear about later on in these in the talks. Particularly the combination between my talk and Gabor Csanyi's talk, which follows on, where we're taking maybe a more brute force computational approach to exploring new materials. So my talk is going to be about random search or random structure search, and I emphasize it as a tool for exploring energy materials. So there aren't going to be a large number of results in this talk. I'm going to focus on how you might use tools such as random structure search or other structure prediction techniques to tackle what is frankly a very difficult problem of dealing with these multifunctional oxides. So just to get started, I think it's important to acknowledge the great impact that the work that Gerd Sieder and others, Stefano Cottarollo and so on in the US, have made in this area. This work that they undertook started in the early 2000s and was really an idea whose time had come. So what they recognized was that over 100 years or so, experimentalists had gathered a large amount of data, crystallographic data, about a very wide range of inorganic materials, and it was sitting in databases such as the ICST in terms of crystal structure files. What they noticed was that developers such as the Cambridge group through CASTEP and the Vienna group through VASP and other codes had developed robust first principles electronic structure codes that could be used in a semi or fairly autonomous manner. And so at the same time, the nature of computing changed somewhat, and it allowed or in fact favored many separate decoupled computational jobs. So the Intel x86 computer chips effectively were giving everybody access to supercomputers, and in fact multi-core machines at that, which meant that very large clusters could be cobbled together in various research labs, but they weren't really the high performance computers that maybe we've been used to in the sense that they didn't enable very good communication between the different cores. So they were best used on lots of separate smaller or moderate sized jobs. So this is really sort of the birth of high throughput computing in the materials sciences, and Gerd Sieder in particular was interested in battery materials or energy materials. So literally the topic of this symposium. And in its turn, this idea of Gerd, which was actually initially named the Materials Genome Project, morphed into a US-wide project on application of computers to accelerating materials discovery, or a renaissance of American manufacturing, as it was called. Now, this was I think it was as I said, an idea whose time had come, but it depended on about 100 years of work from the experimentalists. And once you've trawled through these databases a few times, you might start to wonder, well, what should we do next? Now, at about the same time that Gerd was working on the high throughput approaches, there was another group of us, myself, Artem Oganov, and some others, who were sort of asking the more fundamental question. And that was, what do we do if we know nothing about where atoms sit in space? We've got these, we've convinced ourselves we've got these wonderful first principles density functional theory codes. Surely if they were worth the sales pitch, they should allow us, say, to predict the structure of diamond or more sophisticated or complicated structures. So that's what I got interested in. I was particularly driven to that because early on in my career, I'd been very interested in computational spectroscopy. And it was frustrating that the only way we could really help the experimentalists was if we already had a good candidate for what their structure might be beforehand. And it seemed an obvious step to try and generate computationally some of those candidates as well. So that's the task of structure prediction. For many years, it had been attempted in other ways for many years previously. In particular, it made great impact in the molecular crystal community, where very bespoke models for molecular crystals were developed and a wide range of global optimization techniques used to predict the crystal polymorphism. But in the inorganic structure space, it really hadn't made a big impact, partly because it was depending on the use of empirical potentials. And it turns out, and if I have time at the end, I'll come back to that to set Gabor up for his talk. But it turns out that many of the force fields that were used at that time actually did not have very friendly energy landscapes and were not particularly amenable to global optimization. Whereas the approach I took, which I can't really claim any great foresight at the time, it was really just because I'd been working on first principles density functional theory methods, and I didn't think of doing it in any other way at the time. But it turns out if you use the first principles energy landscape, things become a little bit easier. So rather than, in this talk, it's a relatively shortened talk, so I won't go into great detail, but it turns out that because the energy landscape is somewhat smoother than it could be, it's not necessarily entirely smooth. For example, strongly bonded covalent systems such as diamond offer very many local minima, but at root, the interaction between the atoms are mediated through smooth interactions, either the Coulomb interaction mediated through Schrodinger's equation, which the controlling term being the kinetic energy, which is wanting to smooth things or spread things out through the system. So there's no sudden switching on or off of the potentials. And these smoother energy landscapes are, it turns out, are relatively easier to navigate than they were thought to be. So it was thought that if you search for any moderately large system, then you'll very rapidly be hit by the curse of dimensionality, which means you'd get nowhere, even with a handful of atoms. What I discovered by applying the simple random structure search that I'm going to talk about in the next few slides was actually I could deal with more than a handful of atoms. And it makes a big difference to be able to deal with 2 or 3 atoms or 10 atoms, because if you can deal with between 10, 20, 30, 40 atoms, that gives you access to a very wide range of inorganic crystal chemistry. So what was the method that we came up with? This was work done with Richard Needs, who recognized its importance to high pressure physics. So eventually, we didn't initially call it ab initio random structure searching. It was just what we did to start with. In 2006, we introduced it as part of an application to looking at the high pressure phases of hydrides. But in time, we came to call it ab initio random structure searching. And the basic idea is the following, is that you build what we call sensible random initial structures. And I'll come back in a few moments to talk about what we mean by sensible. And we're mostly focusing with periodic systems here. It needn't necessarily be constrained to that. It could be clusters or interfaces. Again, more about that later on. But for the time being, let's think about crystal structures. So we build a randomly shaped unit cell, roughly the right volume, and then fill it with atoms, with simple constraints like don't put the atoms exactly on top of each other. And then we perform a local optimization. So we move the atoms and the shape of the unit cell until the forces and stresses become 0. Now, I've just written local optimization here. Anyone who's written density functional theory codes or indeed empirical potential codes will understand that it's not completely straightforward to do a very good job locally optimizing unit cells with changing volumes and shapes. It's very important that you do this carefully, and it's very important that you don't stop your local optimization too early. And it can be tempting to do so. For example, if you get stuck close to or on a saddle point or something like that in the energy landscape, it might look like the minimization is finished. Well, you just got to keep going until the energy will no longer go down anymore. If you do that, or indeed if you do that many times, or in fact many times, you can build up a wide range of different locally optimized structures. And then all you need to do is rank those structures according to their energy, or if you're interested in optimizing some other property, you could rank them according to that property. But typically we rank them according to energy or enthalpy if we're dealing with high pressure phases. And if you've sufficiently sampled your configuration space, those lower energy configurations will be the ones that are likely to have been found experimentally. Now, or to be found in future experiments. Now, this is a stochastic approach, and you could always ask the question, how do you know when you should stop? And there's no clear answer to that, but I can give a good answer for when you shouldn't stop. And you shouldn't stop if you've only found the structures you're interested in once. So keep going until you found them many times. And that will give you some confidence that you're not overlooking some relatively smaller basin that in the energy landscape that lays nearby. In fact, yeah, anecdotally, I mean, in many cases, you know, the success or otherwise of a project has depended on whether I've accidentally left the calculations going on over a weekend or not. So you must always be cautious that there could be something lurking out there to be discovered in the future, which also gives encouragement to anyone else entering the field, is that you shouldn't take for absolute granted the published results that have been obtained in these stochastic manners, because something could easily have been missed. Okay, so I'm just going to show an example. I always now include a video of what I mean by random structure searching, because it was pointed out to me by Nicola Mazzari that sometimes it's not entirely clear what's going on. And I think that's because it's really not very much is going on. We're just putting atoms randomly in the unit cell and moving them downhill to their nearest local minima. So I haven't got slides and slides telling you about evolutionary algorithms or particle swarms or the other competing approaches. It's almost like I'm playing a trick on you, but I'm not. Literally what we do is we fill unit cells with atoms randomly placed so they don't sit on top of each other and relax downhill. So what I'm going to show here is an example for a fixed unit cell for historical reasons, really, because this connects to an actual scientific project for gamma boron. So gamma boron is a high pressure phase of boron that relatively recently had its structure determined. And so I've got a fixed unit cell, which actually corresponds to a unit cell that was determined experimentally, but they didn't know where the atoms were. And this was work originally done by Artem Oganov. He used his evolutionary algorithm to determine where the 28 boron atoms should sit. In this example here, I've placed the 28 atoms in the unit cell, and I'm going to relax them. And in fact, I probably relax them, in order to get the result I'm going to show you, I'd have to do it about 200 times. So it's about 1 in 200 times you would get the result that I'm showing you here, which is the atoms, you go around, relax, and then snap into this beautiful structure that Artem discovered, which is a packed icosahedra with dumbbells of boron sitting in between them. In fact, he determined that there was actually charge transfer between these dumbbells and the icosahedra. So there's some nice crystal chemistry there as well. So, okay, so of course I've shown you an example when it worked. You know, the other 199 times I've got some sort of messed up structure at the end of it, or some metastable phase that might also be interesting. Okay, so what are the features of random structure searching compared to, for example, other approaches? Well, you know, when you're doing global optimization, there's always this balance between what's called exploration and exploitation. In random structure searching, it's extremely on the exploration side. And that kind of suits my personality. I want to discover new things. I'm not necessarily worried about finding diamond the quickest and rediscovering diamond quickly. I'd like to maybe slowly find something that no one had ever seen before. So the sampling we're doing is as close as possible a uniform sampling of configuration space. So it can be tempting to say that you might, when you're doing a search, to cluster your samples around the expected values of, for example, some Gaussian distribution around the expected volume. But if you do that, then you're not searching in the corners of the distribution, and that might be where the discoveries lay. So I think it's very important to do this uniform distribution. The random structure searching is intrinsically parallel. The runs are, so this is very important if you want to do, want to run this, want to exploit very large supercomputers. So in principle, if you needed to generate 1 million structures, if you had a 1 million core machine, with random structure searching, you could do it all at once. There's no generations. You don't have to wait for one generation to come through to get on to the next one. You just do them all at once. The runs are uncorrelated. So when I said that the condition for not stopping was waiting until you'd found the structures several times, that is a meaningful statement because the runs are uncorrelated. If the runs were correlated, for example, you're basing the next step on the previous steps, finding the same structure again and again isn't really telling you anything. So this gives you a not stopping condition. But I think also, and I think this is where random structure searching is starting to find its appreciation, is that it fits very closely with the ideas of inorganic crystal chemistry in the first place. So it doesn't depend on biology or bird flocking. The constraints or the way that we set the calculations up are in terms of chemical ideas, and I'll come to that on the next slide. So it comes in through the generation of what we call these sensible structures. And by sensible, we mean structures that are more likely to give you low energy configurations. So there's an element, there is some steering here, there is some biasing of your sampling, but once we've decided what those biases would be, we try to sample as uniformly as possible. So if you don't know anything, the straight random search is the thing to do. Still don't put the atoms on top of each other, and probably you can set the rough volume without too much loss of generality. But once you start to learn more about your system, it can be a good idea to impose chemical ideas such as molecules, fragments, distances, and connectivity. It's very the use of symmetry is very powerful as well. Most crystal structures have a little bit of symmetry, and so it's worth using some of that to speed up the calculations. And in fact, we've had a lot of success by teaming up with experimentalists and sort of combining what they know with what we can find out computationally to speed things up. Now, a lot of the early applications of this were in high pressure physics. I'm not going to go into the applications in detail here, apart from to highlight that the first application, and where we actually published the random structure searching method, was in the search for superconducting hydrides. Now, this was based on the idea of Neil Ashcroft, who suggested that if you added a little bit of something to hydrogen, you might be able to trick it into becoming metallic at a lower pressure than pure metallic hydrogen, and that might lead to a way to generate high temperature or even room temperature superconductors. So we played in this area for a while, looking at silane initially, which turned out to be a semiconductor in this particular crystal structure, not a superconductor, but looked at some other possibilities which were promising. And as years have gone on, actually, this has turned out to be quite an active field. So what this graph here shows is actually a sort of new generation of high temperature superconductors, the superconducting hydrides, which are experimentally confirmed. So the H3S and then LAH10 structures, the H3S discovered by Michael Eremets and the LAH10 by Michael Eremets and a team in Carnegie in the US at the same time, were striking in that both these compositions and indeed structures were computed using structure prediction techniques like AIRS or Calypso in the case of AIRS and Calypso in the case of LAH10 before the experiments were done. So this actually completely changed the game for the search for high temperature superconductors. Now, I'm tempted to use some advanced machine learning techniques to predict how TC might evolve in time. We've got 2 points in here, so why not draw a straight line in? Actually, this is a slide that I've been using slightly cheekily over the last few months. But actually, yes, in fact, today a paper was published in Nature, which showed that this simple prediction has been borne out. So Ranga Diaz and Ashkan Salamat in Rochester and Las Vegas have published and been featured on the front page of front cover of Nature, a new candidate for room temperature superconductivity. Now they take a carbon sulfur hydrogen system of unknown structure, squeeze it to 267 GPa, and end up with a superconductor with a TC of about 15 degrees Celsius. So this is a breakthrough. I mean, it's a room temperature superconductor, unfortunately at pressures close to the center of the Earth, so we still have work to do. So a further bit of technique that we've been developing is so-called manifold learning, which is a way of doing dimensional reduction to describe large numbers of the structures that you generate from a random structure search and visualize them in a lower dimensional space. And so this is some work that Ben Shires has been doing, my PhD student in Cambridge. And here we're visualizing the Lennard-Jones 38 cluster, the famous Lennard-Jones 38 cluster. And the beautiful thing of these projections is that it without any input, presents the multi-funneled structure that had long been suspected for this system. So this is what I think is going to be a useful tool for visualizing these very large numbers of structures that we've been generating over the years. Next slide. The striking thing about this work of Ben's is that it seems that we only need 3 dimensions to do this projection down into low dimensional space. So if you add 4, 5, or 6 dimensions, it adds nothing to the projection, which is lucky for us, given that we can only visualize things in up to 3 dimensions. I think this is probably a very interesting result. For example, the exploration of latent spaces for the generation of new candidate structures. It's showing that there is such a space out there to be discovered, and it's not that high dimensional. So I want to emphasize towards now a couple of things that are very important if you're going to use crystal structure prediction to explore energy materials. So as Peter pointed out, these materials are often multifunctional transition metal oxides of some kind. So these are necessarily ternaries or quaternary compounds. And if you do any structure prediction technique without with no constraints or no initial preparation of the structures, you'll run into the so-called ordering problem, and you'll put the wrong atoms next to each other. So in the case of random structure searching, the way that we do that is we just measure minimum nearest neighbor differences between species and apply sort of chemically reactive hard spheres when we're generating the initial random structures. And if you do that, this is sodium niobate example here. On the right-hand side is a randomly generated sensible sodium niobate structure that has minimum distances that are the same as in a candidate sodium niobate structure. So it's a kind of, it's less a learning algorithm than a teaching algorithm, in that we teach the random search right at the very beginning what corner of chemical space or structural space we want to explore more thoroughly. And this is particularly important, and I'll come in a few slides. I'll talk about interface structure prediction, the work I did with Georg Schusterich. This was particularly important in that case for dealing with the strontium titanate interfaces, which was one of our first applications. So making sure you're not putting the wrong atom next to each other in the initial random structure is very important. The other key thing, of course, is to start exploring composition space. So you want to essentially randomly choose your compositions of your structures at the same time. When you've done that, you need to visualize them in some way to identify which are the stable compositions. Traditionally, the way to do that is with a convex hull construction. In this case here, to illustrate the variable composition space, I'm showing another sheep map that Ben generated for the carbon, hydrogen, nitrogen, oxygen system, which actually rather beautifully, if you look on the right-hand panel, when we embed this quaternary system into a 3-dimensional space, we naturally see the tetrahedron, or the compositional tetrahedron, emerging from the data. So we don't impose the tetrahedron; it just emerges from the dimensional reduction. If we reduce it to 2D, it's squashed down into a diamond, into a diamond shape. So the other thing that's very important to take into account, and maybe this is the most specific and difficult part of structure prediction for these systems, cathode materials and so on, is dealing with the electronic and magnetic structure, because these are systems where actually density functional theory in its most basic form doesn't necessarily work very well. The first thing that you want to do is take into account the magnetic structure. In the case of the materials project, most of the cathode materials were just assumed to be ferromagnetic in nature. That was the easiest thing to do in a high throughput manner. But the reality is that many of these phases are likely to be antiferromagnetic or indeed ferrimagnetic. somewhere in between ferro and anti-ferromagnetic. So you actually need to do another level of structure search on top of the actual positions of the atoms. You also need to search for the magnetic structure. So you can do this in airs, because in CASTEP you can impose an initial magnetic structure. So we randomly generate initial magnetic structures, possibly with symmetry imposed, and relax those structures. And it turns out, whether something is antiferromagnetic or ferromagnetic can make a difference to the energy of tenths of an electron volt or so, sometimes more. I put down here is that at your bare minimum, probably you want to use density functional DFT plus U to describe your strongly correlated electronic structure. But actually, you may well want to go beyond that. And I think this is where the work that Cedric has been doing could really make a big difference to this field. At the moment, we're not quite there of doing structure searches with these methods. We can with DFT plus U, but we haven't yet gone beyond that. But that's an obvious next place to go. So just to finish off, I want to point out that batteries themselves are absolutely stuffed full of interfaces. So probably the key problem is to understand when one material starts and another one stops, and then parts of the material are flowing from one side to the other. So interfaces are critically important to batteries, one kind of energy material. Also want to point out that they're also very important, for example, in nuclear materials. So an example of an interfacial material that we use structure prediction to determine was a suboxide layer in zirconium, which actually seemed to control very much the stability or the lifetime of these nuclear fuel rod casings. So interface structure prediction is probably what we're putting most of our effort on in my group in terms of structure prediction at the moment. And I've had a range of collaborators that have been working on this. Georg Schusterich, when I was in UCL, was postdoc there and joined me in Cambridge shortly afterwards, was the pioneer of this field. So he was the first person to figure out how to put airs together with interface structure prediction. And he predicted some interfaces, or grain boundaries rather, in graphene, which were then subsequently identified in electron micrographs, but also did some very nice work on strontium titanate, and also more recently titanium dioxide, which I think is some work that's under review. I also worked with John Brodolt and Jack Van Dryle on grain boundaries at high pressure, which I think is a massively underexplored area. So we were looking at MgO grain boundaries. With Kazuto Akagi in Japan, we've been looking at strontium titanate reconstructions on the surface. And with Judith Driscoll and Bonan Zhu, who was a PhD student in Cambridge, but has now moved to work with David Scanlon on the same Faraday project, the FutureCap project that I'm working on. We were looking at this fiendishly difficult problem of strontium titanate interfaced with Syria. Now, these calculations are challenging. You have to use everything to help the calculation along in order to generate enough candidate structures to give you a reasonable estimate of the low energy structures. We are not yet at the stage where we can do a blind prediction of interfacial structure. We tend to need to be guided by experiments. So we want to know what the orientation is between the two grains, or the grains and the interfacial material. This reduces the search space and gives us a better chance of success. So just to finish off, I want to sort of kind of hand over to Gabor. I mentioned that I was fortunate in that I used density functional theory throughout in this structure prediction, because it's actually, although it might seem that this was a computationally more costly route to go, actually, if the energy landscape was more benign, the prefactor of doing the DFT calculations sort of disappeared quite quickly. So what I'm showing here is a density of structures, a density of states for structures for silicon, for 8 atoms of silicon, and the white filled in histogram is for density functional theory. And then I've put 2 different potentials, a Reax-FF and a Tersov potential, which have completely different density of structure states. And I think we could probably agree that the DFT is closer to being the reality, the true distribution. And so in particular, this Tersov potential, most of the structures you generate by doing a random structure search are just completely unphysical and not related to ground state silicon. And so the problem with these empirical potentials is that they weren't properly describing the entire energy landscape. They might have been fit well for the bottom of the well, but weren't properly describing what happened when the atoms were in crazy positions. And this is something that Gabor and work with Volker Deringer, we've been trying to put right. I won't say much more about this because I'm sure Gabor will visit it in his talk. So I just want to finish off now by reminding us that if you combine stochastic search with first principles density functional calculations, there's a chance to really discover new things that hadn't been previously suspected. And indeed, we might start to use this as a kind of virtual experiments. And that's actually how I've been using it. I've been playing and mixing and matching and seeing what I can uncover over the last 15 years or so. And then just to point out, the codes I use are all available for academic use freely. AIRS is open source, and CASTEP has a global cost-free license for academic research. Okay, I think I've come to the end now.
Many thanks, Chris. I think we have some time for a couple of questions. So, while people are gathering their thoughts, I might just start with a simple question. But is there any limit in terms of the pressure that you can reach with AIRS and DFT, or does the method at some point eventually break down?
It's sort of the opposite. The limit is zero pressure in a way. So density functional theory, of course, is certainly local density approximation, and the GGAs are parameterized for uniform electrons and slowly varying electrons. And as you go to higher and higher pressure, you tend to head towards that uniform electron limit. So I've done work, I've published work with Miguel Martinez Canales on taking carbon up to a petapascal in pressure, and there's no reason why it shouldn't work at those high pressures. No, the real difficulty is the kind of work that you do is dealing with localized electrons, where you're having essentially high charge density and vacuum all in the same system. So that's the way I look at it, is that the limit is the frontier is zero GPA.
Actually quite a good news and quite encouraging for the future generations. Fran has a question.
Yeah, I have a question, Cedric, if I may. Nick Harrison.
Nick, hi.
As you wish.
Hey.
Cedric?
Is it okay to go ahead? Yeah.
Yeah. Oh, by all means. Sorry, I was muted.
Thank you, Chris. So, Chris, do you have a feeling for the scaling of the random search? So, in the case where you don't have any chemical constraints that you can apply,
yeah. So
how does it scale with the number of atoms? Sorry.
Yeah. It depends on the system. So. Normally when I show this, I show a couple of examples. I show carbon and I show Thomas Fermi hydrogen at very high pressure, and there's sort of two ends of the extremes. So an extremely metallic system, it's trivial to find. You very easily, with just a few samples, find essentially the crystalline solution. It just crystallizes. They're sort of crystal seekers. Mm-hmm. But obviously with carbon, well, we know there are lots of possibilities, so you at least have to sort through all of the sensible low energy possibilities, and then you're going to get all of the, say, amorphous carbons as well. Yeah. So the examples I show would be about 100 atoms of Thomas Fermi metal, and then 20 atoms of carbon. And if I'm doing 20 atoms of carbon to find the diamond ground state structure, it tends to be taking about 10,000 samples. Yeah. It's perfectly possible now. But it's, some systems are just genuinely difficult for a good reason, in that there's lots of possibilities.
Sure. So if you start having multiple atoms in the composition, and relatively large numbers of atoms, then it scales.
It becomes difficult. Hence the importance, for example, in the interfaces, to make use of minimum interatomic distances to order the structures to start with. To make use of knowing the orientation of the interface of the two different grains, and also, if you can, make use of symmetry. That will always allow you to go further. Mm-hmm. But if you want to, so I don't know, a ternary system, maybe 12 or so atoms with not using any symmetry or any distances. But that's still not too bad. There's quite a lot of chemistry you can do with 12 atoms, and if you use symmetry, you can double that up or multiply that up by 4.
Yeah.
Cedric, can I go?
Yes, you can go now. Yeah.
Hi, Chris. Thanks for your talk. Just a question on the interface. Have you tried to study liquid-solid interfaces? Mm-hmm. And if it is possible to have a kind of solvent, and just to see how the solvent. So
I'm wondering. Maybe you're trying to find out how the solvent maybe orders itself on an interface on a surface,
yes,
in the sort of first layer, for example.
Exactly. Or so if the solvent is water, also so the second layer may be important.
Well, so these are all. I mean, a long time ago with Angelos, we were looking at we looked at water deposited on copper surface, and we were able to find the same sort of ribbon structures that they were finding experimentally. But yeah, I mean, I think it would be possible. But again, yeah, bear in mind the number of degrees of freedom you have to deal with. So anything you could do to constrain the search would give you better results.
Okay. So I will write to you about the manifold learning. Okay, so it's a long story probably. Okay. So thank you.
I should mention, Fran, there will be some time for discussion.
May I ask one question to Chris, please? This is Srinivasan from University of North Texas.
Hi.
Hi.
Go ahead.
Chris, I really enjoyed your talk. Question: you used Lennard-Jones for searching for random cluster structures, but using a many-body potential like EAM is not going to be any more expensive. Do you think the effect of many-body terms have any bearing on the kind of structures you would see? Thank you.
Well, so the Lennard-Jones example I showed was the work from Ben on doing dimensional reduction, and the idea for that was that it was fairly cheap for him to generate. Say there was 100,000 samples there. Well, I'm absolutely certain that they'd be different. I mean, that would be you would have different ground state structures for a different potential type. We haven't looked at those potential types, but it would be. Yeah, I think what I'm optimistic for Ben's project in that we start looking at these energy landscapes in a more holistic way, and it would be very interesting to see qualitatively how they changed as you changed the type of potential that you're looking at. Does that sort of? I'm not sure if that answers your question.
Yeah, yes, it does. Yeah. It does. Thank you. Yeah.
I think at this stage, because we are running late, we should thank Chris Pickard very kindly for his outstanding talk. So thank you, Chris. We are going to move now to Professor Gabor Csanyi, who will continue actually and build up on Chris' talk with machine learning of interpotential.
Hi, can I go?
Yes, Gabor.
Okay, so let's try this. Share. Okay, do you see a shared slide?
Yeah, it works.
Okay, good. Okay, so hello. It's a pleasure to follow on from two eminent talks like this. My name is Gabor Csanyi, coming from University of Cambridge, from the engineering laboratory. And the talk is, I want to tell you about machine learned force fields and potential energy surfaces. I only have about 25 minutes, so it's going to be more context than detailed technology. But I also want to give you sort of the news from the trenches, how this is a very fast moving field. A lot of us are very excited about it. So I want to give you a glimpse of what have we achieved over the last 10 years and what are the exciting developments now. So the most important thing is that we've reached a stage with these machine learned potentials that we are not just excited that we can make them. We are actually now in the business of using them for science. And that's nothing gives me greater pleasure than that. So and of course, it's usually my friends, not myself, who have the scientific questions, the materials questions, but the fact that these potentials in so little time have come of age and actually are useful rather than just sort of technical feats is really exciting. And so that also means that a lot of people have jumped on to this train, and there's a lot of benchmarking going on. So there will be the next couple of years a lot of shakedown of which particular approach is better, which is more optimal, and so on. And that's also, of course, that's what goes on in the trench that you don't necessarily see from the outside. But of course, there are also some new ideas. So I hope I'll have time at the end to tell you a little bit more about what we've learned conceptually about force fields and quantum mechanics, because I think that we have learned something that we didn't know, which enables us to really build better approximations. And in particular, I'll tell you how we sort of brought back this idea of body-ordered expansions, 2-body terms, 3-body terms, and so on, which of course empirical force fields have been doing for many decades. Something that I won't have time to talk about in this short talk, but it's definitely very exciting, is how we try to incorporate long-range interactions. Everything that I'll be telling you about is about potentials that are short-range, and we can do a lot with short-range, especially if you pick your material carefully. But a lot of new ideas are kicking about in how to extend that to long-range interactions. So I want to start much further back and this is sort of my standard slide I made almost 20 years ago when I arrived in Cambridge from the US to start my postdoc. And it's really about the multiple scales of materials modeling, and it encompasses, think about it, hundreds and thousands, perhaps millions of people working in a real variety of fields. So all the way onto the left, you have quantum chemistry, and quantum chemists are very sort of earnestly trying to solve the Schrodinger equation. They have, in some sense, the hardest task. They set themselves up to solve the many-body Schrodinger equation, really with as little compromise, as little approximation as possible. And then over the last 50, 70 years, a whole slew of approximations have been developed for the Schrodinger equation, quantum Monte Carlo, density functional theory, and various butcherings of that, all the way to the crudest empirical quantum mechanics, tight binding or an LCAO approach. And as you make more and more approximations, what happens is that you can treat larger and larger systems, and not just because of the prefactors, but scaling. Of course, quantum chemistry at the moment really scales exponentially. Quantum Monte Carlo and DFT, typically cubically scaled. Of course, there are instances where you could reduce that to linear scaling, but with very large prefactors, and that holds true really all the way as long as you're treating electrons. And with empirical tight binding, you can go to thousands of atoms or nanoseconds if you're doing molecular dynamics. Of course, the real cost is some sort of product of the two. But on the left, what you lose, of course, is accuracy. And I had sort of dared to put quantitative numbers, and there are no citations attached to this. This is just my own gut feeling on what sort of processes and what energy errors you can expect when you use some of these methods. But only 1,000 atoms is not a lot if you think about macroscopic, if you think about processes on everyday life length scale and time scale. So really, the hierarchy, the materials modeling hierarchy continues, and you leave electrons behind, and that's the world of interatomic potentials. And then you can treat millions of atoms. And I dare not put an accuracy, really. I put qualitative, because there are certain things that you're not going to get at all, depending on what sort of potential you use. And then you can go, of course, up from there. You can coarse grain and use leave the world of atoms behind, treat entire molecules as single unit until you arrive at the continuum description of the world, which is when you can treat the kinds of system sizes that we encounter every day. And I already alluded to this fact that up to these methods in the green box treat electrons explicitly, and that's when you solve the electronic Schrodinger equation in some form. And let me not say much more about that, except that it's the dimensionality of that problem is really high, right? So the Schrodinger equation is right here, but the object of that, the wave function, is has 3n, for n particles, it has so 3n variables, and even just to hold one of these objects in its entirety is very difficult. So all the way on the other side, if you're doing what I would call true empirical modeling, you use some sort of minimal description, follow Occam's razor and say that if you want to study self-assembly, let's not start with the Schrodinger equation. You might use the absolute minimum description of objects with blobs that attract each other. And what you end up doing is understanding mechanisms, understanding the phenomena that you observe, but you have much less chance of predicting something genuinely new without ever having seen it, because this way of modeling really starts from observations, really starts from the phenomenology. And it's really in this middle point here, which is where what I'm interested in. That's the world of potentials, where you have already the chance to treat millions of atoms, but you still have this idea that you come from bottom up. You still those potentials are still supposed to be some approximation of the real Schrodinger equation. At least the forces on the atoms are supposed to approximate what they should really be. And in that business, you assume that somehow the Schrodinger equation is solved, and you get, for every 3n positions of atoms, you get the lowest energy eigenstate of the electronic system. That somehow is taken as read, and the function that you're interested in is the mapping from the atomic positions R to this potential energy that you get from the electrons. And once you have this mapping, you insert them into Newton's law, and you do geometry optimization, molecular dynamics, and so on. And this, if you can do that successfully with good enough approximation, then that gives you access to structure of materials, stability of materials, molecules, and the various transformations between them. So I mentioned this already, that there's a big step when you leave electrons behind, and one of the empirical signs that you're doing that, empirical consequences, is this big jump here, right? So look at the famous methods that I named, which are all little communities of scientists clustered in each of these, or maybe not so little for DFT, clustered around these systems. The capability is sort of a factor of 10, or maybe even less. And when you leave electrons behind, you jump a factor of 1,000, depending on the potential you use, even more, maybe 10,000. And that's the gain that you have for not treating electrons explicitly. So the objects of the axis, once you leave the electrons behind, or even the electron densities, you're just dealing with atoms. But the question then becomes, what if you're asking the question on the level of atoms? It's really bad if you then drop down to this level to actually answer those atomic questions. So if my question is not electronic, I don't care about the electronic structure, I want to know where the atoms are, then I don't want to answer it here. Now, the big problem is that at the moment, accurate answers to these questions only come here. And that's why, Chris's success came from doing DFT and having smart enough algorithms and big enough computers to answer these types of questions. What happens to the atoms? So if you think about not structure search, but molecular dynamics, what I would like to do is move the atoms as accurately as they really do, but not treat the electrons. So really, this is where I want to be. So I need a method that asks questions on the atomic scale, answers them on the atomic scale, but not at this accuracy, qualitative. I want it at this accuracy, really as close to the ab initio answer as possible. But I don't want to be down here. I don't want to ask the electronic question. And this is really what underlies my entire research credo, if you like. Is this possible, and how is it possible? How can we stick with atoms and ask and answer questions on the atomic scale? To show you that these problems occupy a lot of people, I've collected just two pieces of not even very up-to-date data on where our non-military computing in the US and the UK are spent. So this is a little bit out of date graph of where the computer time that is used on the UK national supercomputer. At that time it was called Hector, and this is a pie chart from one of their reports, and I've colored the various codes. The pie chart is originally by code, and I've colored the various codes by according to whether they are electronic codes, green, or asking and answering questions on the atomic scale, so interatomic potential codes. And you can see that more than a third of UK non-military computing is spent on solving the Schrodinger equation, either electronically or using the or on the atomic scale. If you go over to the US, and this is the Blue Waters computer, on the largest, again, non-defense computer, and this is the chart I found it's a log scale plot of the various codes, and again I did the coloring, and you can see it actually flipped. So now much more of the time is used for interatomic potentials, force fields, and then you come down on log scale. This is now a blow up, and that's where the electronic structure codes are. And the fact that the UK and the US are flipped sort of reflects just history, a little bit of scientific culture, where the big schools of science have grown up around these pieces of codes. But what I want to get across is that a very significant amount of computer time is spent in doing molecular dynamics at some level or another. So I'm sort of here to report to you that after a few years, we have arrived at that point of being able to do molecular dynamics with first principles accuracy on a massive scale. And I want to show you a couple of examples and then open that up a little bit and discuss how we did that. So the first scientific success was on the growth mechanism of amorphous carbon. So amorphous carbon is a technological material. It's on the razor blades, providing a very hard, very sharp coating. It's also on hard disk drives, using, again, it's a very hard-wearing material. But and you grow them by vapor deposition typically, but really there was no model capable of looking at the growth of one of these films. The idea is that you have an atom that's deposited with some incident energy onto a growing film, and of course the atom comes in, it impacts, there's some bond forming and bond breaking processes, and then the next atom comes. And there was no way of simulating this with any semblance of accuracy. The electronic structure codes are too slow. You need 10,000 atom impacts to, and each of them you need to follow for 1,000 steps. So the system sizes are just way out of what DFT is capable of. And interatomic potentials, empirical interatomic potentials, just were not accurate enough. And that was very obvious when you grow a film with an interatomic potential. It has the wrong density and has the wrong tetrahedral, the sp3 fraction. So what experiment shows is that most of the, if you optimize the incident ion energy, most of the atoms are tetrahedrally coordinated, are fourfold coordinated. And in the empirical simulations, that really just didn't come out. So what we were able to do is to have, we now have simulations that can do that. So here's a growing film where each frame of the movie is one impact, one ion followed for several thousand steps until nothing much changes, and then we throw the next atom. So each frame is one of those events, and what you see is a film growing up, and on the right-hand side is the analysis of the structure. So the fraction of sp3, that's the green curve, and you see we're up to sort of 80 to 90% sp3. And that's just going to keep growing. And what you see here, of course, is the very bottom is not representative. It's just normally you'd have a substrate here. We didn't put that in the simulation, so here we just have a couple of layers of graphite. At the top, you have this layer that's mostly sp2, but as it grows, what's the stationary state of this process is about 80 to 90% sp3, which is what one observes in the experiments. So if we go back to this slide, once we have a simulation that's actually credible, which we believe, now we can actually study what's going on. So people have thought before that the mechanism of growth is so-called subplantation. So the incident ion comes in, and that high kinetic energy sort of densifies the structure underneath the impact site. And when you analyze this molecular dynamics trajectory, it turns out that that's not what happens at all. So you come in with this, what happens is called so-called Peening mechanism. You have an atom that comes in with high kinetic energy. The density underneath that impact site is depleted. And there's an annulus, an annular region where the density is increased due to the knock-on effect of that increase. And these pictures show you the change in density, change in local density averaged over thousands of impacts. The star is where the impact is. And you can see that the sp3 fraction underneath, this is then separated into total sp2 and sp3. So underneath the impact site, you have a depletion of sp3, and there's a densification around it. And then one can use this to interpret and understand experiments. So another application is there's no accident that this is another amorphous application. That's where a lot of the low-hanging fruit is here, is to amorphous silicon, where we make a model, we verify that model, again, really for the first time, reproduces the basic experimental characterization of experimental amorphous silicon, which is again another technological material used in very high sensitivity sensors. And so first you can look at calorimetry. So this is we created the amorphous silicon by quenching at different quench rates, and these are fairly high quench rates, not as, of course, not couple of orders of magnitude away from experiment, but there is a convergence here. So if we used, there's a 10 to the, if you use 10 to the 10, even lower, you don't get anything different, and that matches with experiment. So this is calorimetry at as deposited and then annealed energy above diamond. Once we reach this 10 to the 10 K per second, then we get the energetics that that experimentalists measure. And these curves here are structure factors from scattering and NMR chemical shifts. And again, as we reach these, only with these fast but accurate potentials can we reach slow enough deposition rates in large enough systems that that the basic material that we create is credibly what happens in reality. And once we have such a material and such a potential, we can now do things that you couldn't do before. Now we can do new stuff. And here's an image of a 100,000 atom structure created using this slow quench procedure, which we claim is now accurate, ab initio accurate in its structure. And once, for example, you can put it under pressure and you discover that it crystallizes at about 15 GPa to a simple hexagonal structure, which is seen in experiment, but the mechanism of that crystallization is unknown from the experiment. But looking at our trajectory, we discover, and this is going to shortly appear in a publication, you see new kinds of transient phases as before you reach the final crystal structure. So how did we do this? What is this new thing? So it's artificial intelligence, and let me give you my one slide of what is AI. So there's general AI, and that is started in the 1950s when people made first serious computers. And of course, the next thing you want to do is build intelligent robots. Some of you, depending on your age, may recognize this guy. But that didn't really happen. What happened, we didn't get intelligent robots. What we got are expert systems and databases. And of course, they have had a huge impact on our life and technology. Then in 1980s, people invented artificial neural networks. And of course, what we wanted to, everybody thought we could have immediately is intelligent robots. And some more of you may recognize that picture. And that's not what happened. We got machine learning and kernel methods and high-dimensional regression as side benefits. And they have a huge impact on how we do science, and continue. And that impact is still growing. And that's what I make use of. And you can see how this goes. In the 2000s, people are people have invented deep neural networks, and you can guess what they want to use it for, and it may or may not be successful. But the other side of artificial intelligence, broadly speaking, is machine learning, and that's a computational statistics technique that grew out of the 1980s revolution. And really, there are two parts to it: either there's regression or there's probability density estimation, so supervised and unsupervised learning. And supervised regression is function fitting. And the simplest form of that, which did not used to be called machine learning, but now more and more papers are calling it machine learning, like Chris, I think, did half an hour ago, is to draw a straight line when you think that that is the appropriate model for the data. The idea is that we can do that process, but in higher dimensions and with the same sort of careful construction, that if we think that this line should be straight, then we can get the slope. In higher dimensions, if we think that a function should be described by these 1,000 points and smooth enough, then we can get an estimation for what that higher dimensional function might be. And that's what and essentially that's how we make the interatomic potentials. There's the other side of machine learning, which is unsupervised learning, and that's essentially probability density estimation. So it's basically getting functions out of frequencies, and that's very hard. And in molecular modeling, we sort of know how hard that is because it's the same as free energy calculation. So the log of a probability is minus log of probability is an energy. Log of probability in molecular simulation is free energy. And so we have methods to get free energies, like umbrella sampling, but those are really, really hard. So when you think of machine learning and you hear the words supervised versus unsupervised, if you think of obtaining an energy versus obtaining a free energy, then that's sort of the right idea. So how we use this for to make interatomic potentials is as follows. We have some data points in high dimension. We call that a reference database. Very often that comes from density functional theory, a bunch of energies and forces associated with some structure. And they are samples from a very high dimensional potential energy surface. That's the solution to the Schrodinger equation in some approximation. And then what we do in step 2 is we represent the atomic environments, the environment of each atom in some clever way. And then using that representation, we simply do regression. So we learn the potential energy surface as a function of that representation fitted to the data that we have in our database. And we can do that in a number of different ways. I won't detail the mathematics here, but one can do linear regression if you have very good basis functions. We can do kernel regression if we define a kernel between our atomic representations. A kernel is a basis essentially with 2 arguments. Or one can do neural networks. So in neural networks, you have this recursive functional form of your input representation Q. And again, you just change the weights and the biases until you reproduce the input data. But what is that input data? So that's one of the biggest difficulties. And a lot of recent work has been focusing on that, because neural networks and kernel regression, that's sort of textbook stuff. But in order to apply it, you need a database. And so this is work jointly, Chris mentioned this before, with Volker Deringer and Chris himself, where we try to use the random search approach, but at the same time fit a potential to see if we can both discover structures and have a potential that describes them correctly. And we have pretty systems that more or less do this now, certainly for elemental systems. So in this paper, we tried the very same system protocol for carbon, silicon, boron, and phosphorus, and we find the well-known structures but not using DFT random search, using only single point calculations of DFT, having built a potential on the way. So here's an example of that for phosphorus. Here are all the structures that were discovered by random search. Then you use them. We discovered some structures. We also pulled them apart a little bit because we know that people are interested in 2D forms. And then we get a potential that's really quite credible. So we can, for example, use it to run molecular dynamics of a liquid. And when we pressurize, we find this famous liquid-liquid phase transition, phosphorus going from molecular liquid to a network liquid. So I want to finish up by showing you what the problems are and how we might, and I'm really excited about how we might solve them. So all of these machine learning approaches are fitting functions in high dimension. The space we're fitting in is the neighborhood of an atom, which is many dimensional space. And here's the typical thing that happens. So imagine that we're thinking about titanium, and we have some BCC titanium and some HCP titanium, right? So they're just different crystal structures. And we have some data. Let's shake it around a bit. We have some data close to HCP, and we have some data close to BCC. And here on this three-dimensional plot, this is a plot in the space of triangles that exist in the system. Here's my HCP data are the blue cloud points, and the BCC data are the green cloud of points. And now I investigate I fit a potential, and I investigate what it does on the Burger's path, which is a shear there's a shearing transformation on the unit cell that transforms HCP to BCC. And what happens is that our potential, the black is DFT, and our potential that's really very good here and here is really not very good in this as we do the transformation. And that's because there's no data here. So this transformation takes us through phase space where we don't have data. And where you don't have data, high dimensional fits make big errors. So that's that limits the amount of discovery that you can do. So I think we should try and fix this. So this is one attempt, 8 pips, and that's instead of kernel machines, now that we learned a lot how to do this, we go back to linear fitting using polynomials. So here's another example of the same thing. You take methane, and again, we shake it around a bit, fit data just around here, and then we remove a number of hydrogen atoms. So that's something that we haven't trained the potential to do whatsoever. This is what happens if you do that with DFT, different numbers of hydrogen removal. And here's what happens if you do that with a neural network potential called Ani. That's one of the preeminent neural network potentials for organic force fields that's freely available. You can play with it. And it's been fitted over here. And so when you remove hydrogen from it, at least the energy goes up a bit, but then it goes completely garbage. And what happens when you use body-ordered polynomials, so 2-body, 3-body, 4-body functions, is you don't get very super accuracy, but at least you get the right kind of thing. And so this is a polynomial potential that has a 2-body term, a 3-body term, a 4-body term, a 5-body term, and not being fitted anywhere away from the ground state. It has the isolated atom energy. So this black line, the fact that when you remove all atoms together, arrives here, that's part of the fit, because that's the 1-body term. I missed that out from here. But so that's naturally part of this system. But we make these fits using a body order representation, using everything that we learned about how to make high dimensional fits. These are moderate dimensional fits. So this is 1-dimensional, 3-dimensional, 6-dimensional, but not 50 or 100. And that seems to be the best of both worlds. So it's super accurate where we fitted it, and gives us reasonable answers where we didn't. So the way the most modern way to do this is to create these body ordered basis functions. And here's the functional form is super simple. It's just YLM, spherical harmonics, times an orthogonal radial basis, and the n here is how many bodies you have. It's been sort of proposed by these people here, and it does everything that we want. It has permutational invariance because we use these basis functions and project the density of atoms onto them. We have selection rules on L and M, the YLM quantum numbers, which involve, which gives us rotation invariance. And it seems that this way of doing things gives us the extrapolation that we want. It's really fast to evaluate. I'll skip the actual numbers, just that these things converge. So if we increase the body order, we get better and better accuracy. But the really interesting question is, why are we just now doing this? Why could people knew what YLMs are? This sort of mathematics here is very old. And I think the reason is that we've learned not to be afraid of lots of data, not that is actually doable. And that of course happened with neural networks first, but now that we know that based on a couple of thousand DFT calculations, we can make an accurate potential, I think we can sort of go back to simple functional forms like this one, and really do this very, very precisely. We also understand regularization. So when you do a linear fit with basis functions like this, there are sort of textbook mathematical tricks that we need to invoke. So I want to finish on a note which is about understanding. And if you think about empirical force fields, or the organic force fields that people use to simulate large organic systems, they have these body order, but they have these 1D parameterizations. That's their big problem. We have these nonlinear ML potentials, the kernel methods, the neural networks. Fine, they don't extrapolate very well. The quantum chemists have systematic expansions, but of very small molecules, but they scale exponentially. So that's why you haven't heard of them. And then, of course, there are molecular models that are very close to these nonlinear ML models, but again, they're not extensive, non-transferable, but systematic. And what we've understood just over the last year is that all these things can be kind of put in on the same footing. So if you do nonlinear regression, but make this basis set smaller, you go from here to here, formally even. If you drop the nonlinearity and do linear fitting, but with clever basis sets that are not dissimilar to the ones used here, but more complete, you can do linear ML models. That's what I've been showing you. The APIPs, these are the curves that I had on my slide, are actually versions of the quantum chemists models, but made systematic, and atomic body order is used, whereas it wasn't used here. But it turns out that they are the same as really empirical force fields, as long as you free up the functional forms. So instead of Morse or quadratic, you use polynomials. And it turns out that these way of doing body ordered force fields is actually the same as what people have been doing with linear ML modeling. So these things are closely related. So almost everything that's been done in force fields over the last 50 years fits into this framework somewhere. And once you have a framework, a mathematical unification, then of course you can figure out what to do where and what is optimal. So that's all I had to say. We can go back then. We have these new technologies. We can go back to doing physics. And I'm really looking forward to doing that, and hope some of you are inspired to come with me on that. Thanks very much.
Brilliant. Many thanks, Gabor. We have time for a couple of quick questions. Just give some time to people for gathering their thoughts.
I'll leave the share on just in case people have questions.
Yeah. Just in the middle, I had a very fast question, Gabor, a more general one. How do you think the field might progress in materials modeling in terms of other progress made in the field of AI? Or if you want, do you think that there are future progresses in AI that will dramatically impact what we are doing in materials modeling? Or you think the two are kind of separated somehow? I don't know if my question made any sense.
No, yeah, it's funny, right? Because I think where we ever, what I showed you wouldn't have happened if we weren't having the AI revolution. But that's a social thing. Mathematically, if you look at what we're doing, it doesn't need AI really. The funniest thing is when, and you can sort of see the the sign if you look hard enough. I'm on the bandwagon. I wave around the machine learning banner just like everybody else. But you know, when you look at deep neural network model of blah in materials modeling, and you look at what deep is, it's usually 3 layers of neural network of three layers in your neural network. That's not deep. A 3-layer neural network, if you could reduce it down to 1 layer, that's a kernel method. And most people who do a 3-layer neural network don't reduce it to 1 because they don't have good enough descriptors. Whereas the real revolution in AI, the actual revolution in AI, is deep neural networks with 100 or 1,000 layers. And those are the things that will drive your self-driving cars and let you in the border by recognizing your face. But that's a different, totally different engineering technology. So those tasks, that's the revolution. That if you have no idea what the right descriptors are, as we don't for images and sound, and then the 100 and 1,000 layer neural networks will do it, and nothing else will. But I don't see that in materials modeling. We know what the right basis functions are, and the proof is that we can do linear fitting, and it's just as accurate. And if you look at the benchmarks that are slowly coming out, neural networks always lose by a little bit. Whereas it's complete opposite to the image recognition, sound, you know, that there with image recognition and very complex tasks like that, deep neural networks absolutely win, hands down, no question. They leave everything in the dust, everything else, every classic engineering signal processing method. But in materials modeling is the opposite. So you can think that neural networks and these very AI-inspired methods are exciting and sexy, and that's what you want to lose. Just be prepared to not do as well versus another method that actually uses quite a bit of chemistry and physics, developing a good basis set and doing a linear fit. But we wouldn't be here if it wasn't for Jörg Behler's 2007 paper on the neural network potential, because people didn't attack this problem, because nobody believed that you could make an ab initio accurate potential. And the social question to ask is, what would have happened if you took the mathematician who understands polynomials and spherical harmonics and representation theory in 2000 and put them in a room and say, make me a potential? They would have done it, except you couldn't get them to the room because they said, this is not a tractable problem. It's not interesting. I'm going to do something else.
It's quite interesting for the future of the history of science as well, I suppose. We have 2 questions coming up in the chat. So we have Charles first, and then Lijin.
Well, thank you very much for the lecture. And actually, my question is kind of concerned about this classical force field that actually whenever we try to project the high dimensional parameters, so degree of freedom, onto this lower dimensional empirical force field parameters, we lose certain degree of freedom. And this might be especially true if we consider the magnetization systems, that if we have iron, for instance, that maybe the spin, high spin or low spin is actually depending on the distance or John Tyler or other stuff, but I can never really find a corresponding degree of freedom of parameters to describe this kind of thing in the classical force field. That's, yeah, do you think it's possible to implement this kind of?
I think not only is it, I mean, you're absolutely right. Not only is it possible, but that's the right way to do it. So absolutely, and there are classical potentials that have spin degrees of freedom. So there are people who are trying and who have done made classical potentials with spin-spin interactions. And if you want to investigate the magnetic transitions, I don't see any other way of doing it, because those spin variables is where the entropy happens. I mean, that's why you have a phase transition. You need the variables which are the critical variables for that to happen. Now, you see some classical potentials for iron without magnetism, and that's okay as long as you're not interested in changes in magnetism. So we have a machine learned potential for ferromagnetic iron, because that allows you to do some mechanics, firmly staying on the ferromagnetic potential energy surface. But of course, if you have any reason to believe that any of the phenomena that you want to study involves a change in magnetism, then that's not appropriate. And you know, one of my boxes here is that once you have these fitting tools, those people who want to study magnetism should use these fitting tools to bring in the spin as a degree of freedom and use it to fit. That it's a bit more involved. You need spin constrained DFT to get the data, because you need data on varying well-defined spin for the same geometry, so that you can probe the potential energy surface. But those codes exist, and there are some people who are doing that.
Yes. Then the question is more like, technically speaking, we are trying to find the global minima of the fitted parameters, but in practice, it's actually never happened. That we actually, in classical MD force field, we always use some nonlinear empirical equations. But do you think is there any tools to help to, let's say, find a better force field, not only to fit higher level of AB initial calculations, but also, let's say, select fitted parameters?
So are you asking whether the fitting process itself, whether we find the best parameters when we do the fit? Is that what you're asking?
I think in practice, sorry, my point is there other ways rather than the fitting itself that we can help to select the parameters?
So in my own work, one of the reasons that keeps me away from nonlinear fitting is precisely that you never know where you are in parameter space. With linear fitting and kernel fitting, the fitting process is the inversion of a matrix.
That's
so
right.
It's completely deterministic and well defined. So that's a huge advantage of those more traditional methods for making fits. Is that you never have a headache. Once you have your data and you have your construction, the parameterization of your potential, the potential is just a deterministic outcome, and it's just a linear. You make a call to your LAPACK library, rather than nonlinear fitting, where it's a huge headache to find parameters. So that's I think is a huge advantage of linear fitting techniques that I mentioned.
In the spirit of time, we are going to take two rapid next questions since we are running late. So we have Lijin next.
Okay, hi, that's a very interesting talk, and I just got one.
I can hardly hear you. Can you speak up?
Is it better now?
Not really. Let me turn my volume up. Try again.
Okay, so
yes, now I hear you properly. Good.
Okay. I just a quick question, and it's more practical. So, how do you prepare the data set to cover the vast conformational space?
So, I think that's really a modeling question, because you have to ask you have to have a data set that covers at least certainly when you have nonlinear models rather than the polynomials that I talked about. When you have kernel methods or neural networks, you really have to cover everything that you'll be interested in. And I'm a great proponent of iterative fitting. So you you do some example of the process. Let's talk about the amorphous systems that we discussed. So I know I'm going to be interested in amorphous carbon or silicon, very large systems. I, of course, can't get data on the large system, but let's say that I'm going to generate small amorphous unit cells, 50 to 100 atoms, by some rapid melt quench procedure. So let's do that a few times, collect some data, fit a potential, and then we do that same procedure with the potential. And early on, the potential is not very good, so that will give us nasty unphysical configurations, but it's important to know that those are unphysical, so they go into the data set, and then you just iterate. And the papers that I cited, with Chris and Volker Deringer, go through this in some detail. So how you explore, you fold back, and you improve your potential, and essentially you can converge. You do this until your potential and the predictions of your potential don't change. For the typical procedure that we had in that NPJ paper is about after 10 iterations, you've discovered all the known crystal structures, and your description of the amorphous state is pretty decent. After 15 iterations, you're done in that elemental system, using smart initializations of these random search using Chris's software tools. So that's, I think, iterative fitting is the way to go here. But you have to always be mindful of what you're going to do afterwards, right? So, for example, if you do all your database is at atmospheric density, and now you want to study high density, high pressure systems, it's going to be rubbish. So you need to make sure that your database covers the diversity and diversity of atomic environments that you will be dealing with.
Right. Thank you for your answer.
We'll take the question of Fran.
So was exactly again on the reference database, and Gabor has already answered, so I'm fine, thanks.
Oh, brilliant, thanks. So I would like to thank you, Gabor, a lot for your outstanding talk and for this very nice contribution. I'm sure everyone really enjoyed it, so thank you again. We will take a quick recess of a couple of minutes before we move to the talk of Jarvist Frost. And I apologize, Jarvis, for the slight delay that we are accumulating. So I suggest that everyone just prepares a cup of tea or coffee before we jump with Jarvis. And maybe you can start sharing your screen. Brilliant. You're ready.
Okay, well, thank you very much for the opportunity to speak here and for organising this, in particular, Cedric. So I'm going to talk about large polarons, and I guess the first thing I should do is really motivate why we should be interested in polarons at all. And the answer is that semiconductors sort of turn up everywhere in energy materials. And most of our semiconductors are generated by very high temperature processes. And so this is an example of pulling a silicon ingot out of a melt. And so this started as a very small scale production just to make individual transistors. You can just see the ingot there, it's about sort of an inch across. And over the last sort of 70 odd years, what we've now done is massively upscaled this production, but really sort of the technology is still the same. So it's very high energy investment, a very slow process to generate these semiconductors. And then when you look at an application such as solar cells, you need a very large area of this semiconductor. And so this picture in the bottom left, the satellite image, if you look at the scale, that scale bar is 1 kilometer. This is now the largest solar plant in the world. It's in India, near the Pakistan border. And so all of that semiconductor material has been made with these sort of high intensity vacuum-based processes. And that's entirely thanks to sort of engineering improvements over the years that they've actually been able to get cheap enough that you can sort of do these things at this sort of scale. So what would be much nicer is, rather than sort of spend a lot of energy making these very high purity single crystals, is to instead be able to use much more variable materials, ones that are synthesized much quicker and much easier. And what you will have there is something that's inevitably going to be a lot more irregular. So if you make something with sort of a solution-based process, it's unlikely to be perfectly periodic. There's going to be sort of defects in there. And yet a lot of our solid state theory, which sort of developed in the 1950s, is based on this fiction of periodicity. And so you need your lattice to be infinite in all directions and to have perfect registration. And then you have a crystallographic momentum, which is a good Q number. And the other sort of issue that we have, I guess, is that sort of recently, particularly since the 1980s, we've got very, very good at sort of calculating matrix elements. So that's that object between in the Dirac-Bras notation, which is then squared. But then in terms of what we do with the output from these calculations, if we actually want to link to experiment, we typically just use Fermi's golden rule. And so this is a first order perturbation theory from solving the time-dependent Schrodinger equation. And the reason we do this is that actually it's quite difficult to do anything that's more sophisticated and sort of further on, but there are limitations here. So what this means is that we're often limited to only being able to model things where this coupling is relatively small because it's a perturbation theory. And so the particular material system, which I'm going to discuss a little bit further in this talk, are these lead halide perovskite class. So this is solution processable, and you can just essentially just mix two liquids together and it precipitates out as a semiconductor. And what this means, because it's very low energy used to actually synthesize the material, it means it's very low energy to rip it apart again. And so it's very, very soft. And so it's crystalline, but if you actually simulate the molecular dynamics, and so this is doing ab initio molecular dynamics with a DFT functional, you see that it's just incredibly large amounts of motion. So the thing is sort of continuously distorting and arranging. So really, rather than sort of being a sort of traditional picture of a sort of a crystal, which is sort of a solid lattice that's sort of basically there at room temperature as if it were a 0 Kelvin, you've got something that's basically a jelly. It's just somehow being held together in a sort of rough crystalline alignment. And if you try and analyze some of these outputs from the MD, so this is now just plotting the iodine locations within a 2x2 supercell, sort of projecting them onto the plane, you can sort of understand what's going on with these sort of 1970s theories of perovskites. So you can think of the material sort of distorting in terms of laser tilting. There's a lot of additional processes going on. So it's a very soft, continuously rearranging and distorting material. So a slightly cleaner way of sort of representing this motion is to do a lattice dynamic calculation. And so here you are basically just doing a Taylor expansion in the potential energy around its optimized location and sort of truncating that at the second order. And then you have a load of force constants that give rise to harmonic motion, and everything sort of behaves itself again now. So because it's harmonic motion, all of these different modes do not interact with one another, and you can sort of plot them as a band structure and so on. And the other sort of thing that's going on in these soft materials is if you have a sort of more complicated semiconductor, so actually move away from just using just pure silicon or germanium, you start having sort of heteroatoms in your material. And all of these atoms are going to have slightly different electronegativities, and therefore they're going to start pulling electron density around in the material. And this is going to give rise to a polar material. And if you combine a polar material with a very soft material, and that means that these frequencies on the denominator of calculating the static contribution to the dielectric constant gets very, very large. And so in this material, so this is now plotting the dielectric function across frequency, and you see that there's sort of a large number of contributions from all of these different phonon modes. And so this contribution, this polar interaction, means that the lattice will be interacting with any charges, including any charge carriers. So any electrons or holes that you have in your system will actually start polarizing the lattice, and the back reaction from the lattice will actually try to trap the particles. And so this is actually easiest to understand if you take the limit of what's known as a small polaron, which is where essentially sort of the electron's kinetic energy loses. So the lattice manages to fully confine the electron density. The wave function is just sitting in one sort of part of the lattice, it's not going anywhere. And there you have this sort of bathtub potential. And so what's going on here is that in the region where the electron density is localized, the ionic part of the lattice cannot respond to the motion of the electron because it's moving too quickly. And so you just have an effective dielectric constant, which is the optical dielectric constant. Whereas beyond the envelope of where the electron is localized to, sort of the lattice can fully sort of reorganize. And so you end up with a sort of polarization cloud that points in and it localizes the electron. However, this is only the case for systems where the driving force for confining these electrons is very, very large, and the sort of electron is unable to resist this sort of collapse, which corresponds to materials where the effective mass is very large, and so it doesn't have the kinetic energy to be able to beat back the lattice. And so to cope with materials where that's not correct, and instead you actually need to consider both the motion of the electron and the lattice at the same time, we need to sort of simplify the theory first. So we can't just go straight away to an ab initio theory of these things. And so we sort of simplify back to this very, very simple effective Hamiltonian, which is given at the bottom, which is due to Ferroelectrics in the sort of 1940s and 1950s. And here you just have a single effective mass electron, which then interacting with a harmonic lattice vibration, so all these bosons, coupled via this long-range dielectric coupling, so just between the electron interacting with the infrared activity of the individual phonon modes. So the Hamiltonian is very simple. You can parameterize it with this sort of dimensionless alpha parameter. And usually if you sort of read sort of descriptions in the textbooks, this is sort of very much considered a phenomenological quantity. However, you can actually just calculate it from doing ab initio calculations, and what it relies on are these dielectric constants, and then sort of a frequency of an effective phonon mode, which you can get from your lattice dynamic calculations. And of course, you also, because it's an effective mass theory, you input an effective mass. And for most semiconductors of technological interest, so these first two ones given on the table on the right, gallium arsenide and cadmium telluride, even though those are polar, their overall alpha parameter is really quite tiny. And that's because the materials are rigid. And it's only when you go to things such as the oxide perovskites that you get sort of really large alpha parameters. What's unusual about the lead halide perovskites is that they exist in a sort of intermediate regime. So their alpha parameter is about sort of 2.4. And sort of a slight additional complexity is the alpha is 2.4, but also the frequencies, the phonon modes, which are representative of the motion of the lattice, are very low in energy. And so even though this Hamiltonian looks quite innocuous, it's still really quite difficult to solve. And that's because it's actually a quantum field theory problem. The reason being that even though you just have a single type of boson oscillation, so the phonon mode within the system, you can create and annihilate as many as you want. And so you have an infinite field of phonon excitations you need to consider, all interacting with your single effective mass electron. So luckily, this is somewhere that the path integral approach to quantum mechanics works really well. And this was, in fact, one of the sort of examples that Feynman himself actually worked on back in the 1950s. And so you have, this is now the Hamiltonian from Ferroelectrics written as an action in the bottom right, that S equals thing. And you have a sort of typical term that looks like it's sort of a Coulomb interaction. So it's got a dimensionality 1 over R with the distance between the electron and the excitation. This still isn't actually simple enough by itself. So you want to solve it with path integrals, but you can't. You can't do this path integral integration. And so instead, what Feynman found to do was that you could build a variational theory. And so to do that, you actually factor a model action out, which you match to the true action, which describes the actual electron-phonon interaction in the lattice. And you replace what you still is too difficult to calculate and to integrate over with its average. And once you just replace the original action minus the model action with its average, it factors out of the integral. So you only need to path integrate your model action. And by the convex nature of the exponential function, you know that this is going to give you a variational theory. And so for the model action, what Feynman proposed was using this quite simple soluble form, which has just a quadratic, so a harmonic term, which actually sort of binds to the electron to some kind of fictitious particle that it's interacting with. And then you also include some kind of tunable dampening. And now this sort of dimension that looks like time is actually kind of a fictitious time. It's not really genuine time. And sort of the surprisingly nice thing about this method is it's not actually just a substitution of the action with the model action, but you're still including always this sort of this expectation of the mismatch between the actions actually in your theory. And so practically speaking, it's a variational theory, so you tweak your two parameters to lower the energy overall. And once you do this, you've actually just specified a quasi-particle state. And the quasi-particle state has actually a very simple interpretation. It's your original effective mass electron connected via a spring coupling to an additional mass, which is the sort of additional phonon drag term, which includes all of the sort of creation and annihilation of all the different actual phonon states interacting and backreacting and so on. So this is really quite simple to then build on top of, but included in here are all the physics of all of the electron-phonon interactions mediated by this electron-phonon coupling term up to all orders in terms of the diagrams or in terms of perturbation theory. And so I guess this is where I actually did something. It was quite minor, which was just to sort of go back to these sort of physical review papers from the 50s and 60s and sort of re-implement the methods in a modern programming language. And this is a very nice programming language, which I recommend anyone who does programming, which I guess is everyone who's listening to this talk, has a look at. Because it's very easy to represent sort of the maths that you find in a physical review paper very closely to what you see in the code and still have it be very high performance. And in particular, I use this sort of fairly modern and mostly developed and sort of refined in the context of machine learning technique of automatic differentiation. So automatic differentiation is a way of getting gradients of functions where you don't actually have just the gradients programmed by symbolic differentiation, and yet without having to do finite differences. It's sort of an in between the two sort of areas. And what it means is that if you can get gradients, of course, your optimization problem is much more tractable because you know which direction in sort of space to go to sort of minimize your function. And so that's just very quickly describing what the method developed by Feynman does. And then I'm just now going to actually sort of describe some sort of applications to different areas. The first one is just to actually consider this sort of the Ferroelectric model simply as a sort of, a simplified physical toy model and see what it can tell us. And one of the interesting things about it is that sort of almost all other approaches to describing mobility are actually semi-classical. They almost always build on the Drude model, which is this sort of picture of electrons literally sort of pinging around within a metal, sort of bouncing off the iron cores, so sort of motivated by the sort of classical gas picture. It was slightly patched up in the 20s to make it compatible with quantum mechanics. And so instead you think about sort of a much smaller electron density on your Fermi surface being scattered between different sort of crystal places of momentum, but it's still just semi-classical. It still just relies on sort of a rate equation, some idea of sort of a discrete classical particle moving between these quantum mechanical states. So as an example, this is actually a very nice study from literature recently, where they went to an awful lot of effort to calculate really quite difficult matrix elements. Then after they do sort of these sort of very in-depth computations with sort of density functional theory, calculate a load of matrix elements, and these have to be over a double Brillouin zone integration, because you have both the sort of the phonon Brillouin zone and then your electron Brillouin zone. Then you take all these elements and you just put them into Fermi's golden rule. And so that seems like a bit of a waste, really, of doing a lot of sort of quite difficult calculations. And also what's typically found, not necessarily in this particular study, is that if you go to all the effort of actually sort of calculating these relaxation times with ab initio techniques, the errors actually build up from all of your different sort of integrations over Brillouin zones, and your perturbation theory sort of add a lot of noise. And so what you often find is you actually get better results just by sort of taking what's known as the relaxation time approximation and just using sort of some fairly standard relaxation time that just describes the whole typical behavior in that class of materials. And this is actually fairly predictive as long as you're looking at a semiconductor that's been sort of, part of a class of materials which is very well understood. However, if you're genuinely trying to just predict new semiconductors or just sort of go off into different parts of the periodic table and try and sort of find out some new things, try and find some materials that might be of interest for renewable energy applications, it's not necessarily so useful because you're not guaranteed that sort of whatever relaxation time that you know from sort of silicon and germanium is going to transfer over to these new materials. And so last summer, sort of this very heavy calculation was done by Andrei Mashenko and Nikolai Prokofiev. And so they have sort of developed these diagrammatic Monte Carlo methods of studying sort of quantum systems to order perturbation orders. And in this work, they sort of introduced an additional Monte Carlo method of predicting mobility. And the thing they were particularly trying to look at was the breakdown region where sort of these semi-classical theories no longer hold. And so in that regime, sort of your Drude-like model is no longer correct. And you start having sort of basically quantum mechanical and therefore sort of undulating behavior of mobilities as a function of both temperature and frequency. And so a question I had was, how well do these sort of 1960s techniques, which essentially, take no real computer time to calculate, compare to this very, very heavy diagrammatic Monte Carlo method? And so this is now going to this sort of 1960s work, which sort of builds on Feynman's 1950s model with a sort of an influence functional that describes the sort of the low field motion of the polaron state. So it's not variational, you're only using an approximation here, but it's still fully quantum mechanical and actually includes all perturbation orders. And so there's a bit of a technical challenge or a numeric challenge, is that sort of the thing that you've got to calculate, which back in the 60s they mainly did by taking sort of asymptomatic approximations for either like low temperature or sort of projecting back to sort of the DC value, is quite sort of ugly. It's quite doubly oscillatory. So you've got these two sort of cosines sitting on top, and you've got a denominator which is exponentially decaying the overall thing, but not very quickly. So it's just the numerics are quite nasty, and currently I haven't sort of fully solved this. Instead, I've just sort of used, you know, relatively speaking, sort of brute force in terms of evaluating millions or billions of data points. However, you start to get sort of behavior that's really quite similar. So on the right, I'm always showing the diagrammatic Monte Carlo results, and also on there, that red trend line is just the semi-classical answer. So when you just take the sort of scattering time approximation. And as you sort of go through sort of all the different things that Mishenko did in their paper, you can find that you sort of reproduce the sort of ski slope behavior of mobility as a function of temperature. One nice thing of this method is because it's, you know, you're just directly evaluating integral, is the sort of the error bars on the left are smaller than you can see. Whereas with a sort of diagrammatic Monte Carlo method, because it's Monte Carlo and it's very costly, you're sort of limited into quite large error bars because, you know, you're running out of computer time. And you can also see that even if you look at this sort of quite difficult case, since this is where this unitless parameter alpha is at 6, which is exactly where the perturbation theory completely breaks down, is you can get these sort of, you know, unusual oscillations in the mobility as a function of the applied frequency, which more or less reproduce what they get with diagrammatic Monte Carlo. So that was quite sort of reassuring, and I felt quite interesting. And so now I'm going to sort of go back to the hybrid halide perovskite system that I introduced earlier and try and sort of predict some actual features for it. And the first one is temperature-dependent mobility. So this is of, you know, massive technical interest. And on this figure, the smooth curves, of course, are the calculated ones. And at the time I did this work, which is about 3 years ago now, there was this temperature-dependent data from a group at Oxford that was on a polycrystalline sample, which is why the mobility is quite a lot lower. And then there were 2 data points for a single crystal sample at room temperature. And overall, I was actually really quite pleased with the agreement here. I mean, you always expect, if you're only considering a single scattering process, which is the electron phonon scattering with a sort of certain method, that you should give a sort of a high approximation to the genuine mobility. And so the fact that sort of, you know, most of the results were below was quite reassuring. One thing that was slightly missing was if you take that same data and then plot it on a log-log scale, you can start to extract an exponent. And this is often used as a sort of a way of understanding what's going on in terms of the scattering processes in the material. So if you can go and look up from these sort of semi-classical theories, what the sort of the exponent should be for different types of scattering. And the experimental data was sort of, you know, depending on how you plot the noisy data, you get an exponent of between sort of -1 and -1.5, whereas the sort of the polaron theory at sort of, you know, large-ish temperatures was very clearly sort of telling you should see an exponent of about -0.5. So that was kind of in disagreement there. But it's very reassuring that about a year later, there was a follow-up experiment by the Oxford group where they looked at sort of a slightly different material, but they seemed to get sort of slightly cleaner data on this, and they extracted an exponent which perfectly agrees with the Feynman polaron theory. So one of the other nice things about these quasi-particle theories is you have access to all of the quasi-particle behavior. So in particular, you can get sort of a renormalization of the effective mass. You can calculate a sort of a scattering time constant. So like these sort of semi-classical ones that are calculated in ab initio mobility theories. And that also sort of tells you, you know, how fast energy can actually get lost from this polaron state. And you also have some idea of how localized the electron is in these systems. So this is sort of dynamically and continuously being relocalized into something that kind of looks a bit like a sort of Gaussian wave function. And so why does this work? You know, it seems like you kind of cheated in a way because you've done something that was really very simple, didn't cost that much computationally, and yet it's given you a completely, you know, temperature dependent with no empirical parameters prediction of the mobility that agrees with reality. And so my kind of answer is that sort of in a polar material, the majority of the electron phonon coupling is going to be via this long range dielectric. So actually using this sort of, you know, quite coarse method, you get sort of, you know, 80 to 90% of what's going on. And additionally for this material, you would imagine that perturbation theory is probably still okay because the alpha is only 2.4, but because the material is so soft, the effective temperature in terms of the phonon energies versus the temperature is very high. And so all of these sort of complicated effects of sort of, not just generating phonon excitations from your electron, but the phonon excitations are being absorbed again by the electron in sort of higher order diagrams, probably contribute quite a lot to the mobility. And so having some genuinely finite temperature mobility and actually including the scattering processes to all orders is probably more important than actually getting the details of the matrix elements correct here. And so one question is, can we do high throughput prediction? And sort of the slightly qualified answer is, yeah, it appears so. And so this is some work mainly done by Daniel Davies, who is doing his PhD in Aaron Walsh's group. And the paper, they were mainly looking at sort of lots of different possible semiconductors, but we also calculated some mobilities with this theory. And it seems it's perfectly set up to sort of, do these quite large scale predictions of mobility. But then the big question is, what do we validate this against? Because, you're not necessarily going to go just off the back of this one calculation to get an experimentalist to try and synthesize one of these things and then go for the sort of very arduous steps of actually getting a good understanding of the mobility. But what else can we do with this model now that we have it? And so one thing that turned up in the literature was trying to understand why the semiconductor appears to have very slow cooling of its photoexcited states when you excite above the band gap. And we sort of just suddenly, as a result of the work that we'd done, sort of had basically all the pieces we need to put together. And we had a model that, okay, you're exciting above the band gap, then we know that you've got these sort of polaron states. We can extract a polaron scattering rate from the Feynman theory, which we can then convert into an energy rate. And we also have some kind of idea of the localization of the polaron. So the ansatz was that you're generating a state which very quickly localizes. It's retaining the additional energy that it has above the band gap. And that then sort of thermalizes into the state and then will of course, diffuse away into the lattice due to thermal conductivity. And sort of another piece of the puzzle from some other work which we had happened to have done was that this semiconductor has an incredibly low thermal conductivity compared to other more standard tetrahedral-like semiconductors. It's about 2 orders of magnitude lower. And this is because the phonon-phonon interaction is quite strong. The phonons are fairly anharmonic. And therefore, the thing's almost like a phonon glass, like it really doesn't like conducting heat. And so combining this together, you can actually from your polaron size, you can define a Mott transition for these polaron states, which also explains why very different data is seen at low fluence when you're not generating many of the polaron states at once, and when you hit it very hard with a laser, when you have lots and lots of polarons. And you can explain a lot of the the change in the physics that you see just by the fact that you're no longer having discrete polarons, but instead they're starting to overlap. So to make it slightly more quantitative, I was approached by some people in the group of Artem Baklin who'd actually been measuring the conductivity of the polarons effectively of this material with a very clean 2-dimensional spectroscopy method. And it took some backwards and forwards and quite a lot of collection of data and just to explain the experimental difficulty. Each of one of these data points on this figure in each of these subplots is quite a serious measurement really. Obviously you can look at it as a function of the different laser intensities, but it took a long time to get this data. And what they were measuring was how the cooling rate, which they could probe quite carefully, changes as a function both of the fluence intensity, so how hard you hit it with a laser, and also how it changes with the material properties. And the 2 things you can extract from here are the slope of this line and its intercept on the y-axis, which we effectively explained just by describing the rate of cooling by this polaron scattering rate. And so on the left, you can see the experimental values, and on the right, you can see the theoretical ones. And then the actual slope, you can actually just explain by a combination of the heat capacity of the lattice and the polaron size. I was very, very happy with this kind of agreement between theory and experiment. I don't think the experimentalists were so impressed. And so I'm running quite low on time, so I'm just going to go for these last few bits quite quickly. So this one is on how do polarons scatter. So if you look at a textbook answer for all of these different scattering rates, and you follow them back in the literature, you find eventually they almost all build on the Born approximation. which assumes a weak scattering, and that the input and output states of your charge carrier are plane waves, the block states. And these rates actually underlie almost all device physics models. You know, they just end up everywhere, basically. And of course, if you have a highly localized polaron state, it doesn't look like a plane wave. And so luckily, this problem has turned up previously in the context of accelerator physics, where they were trying to sort of bunch electron beams and make them quite localized in a sort of Gaussian wave packet. And the addition that you need for your Born approximation is you basically just put in your transverse wave function, so your envelope function, before you do the Fourier transformation to calculate the scattering rate. And so if you put this in, what you see is that suddenly polarons will scatter differently to block states. And there's two real additional attenuations which occur beyond just the one of the dielectric constant, meaning that you're screening the polarons from any defects in the system. And the first one is the classical contribution from physically localizing the electron into its wave packet. And perhaps the more interesting one is you actually get a quantum contribution. So this is because your Gaussian wave packet is incoherent, and so it can't actually support the interference, in particular to allow the electron to reflect backwards. So what you find is that it's very, very difficult when you have when you form a polaron state, which looks sort of a little bit like a sort of a Gaussian, to have a sort of a backscattering reaction. And this is of particular importance, of course, when you're thinking about scattering in terms of transport, because any sort of backscattering reaction is the worst thing you can do in terms of limiting mobility. And yeah, and just these figures, of course, were developed for the case of the lead halide perovskite. So finally, and very quickly, the polaron renormalized phonon modes. So you have this quasi-particle state. It's a simple harmonic oscillator. And so what does that mean? Well, the state that you're simulating is actually the transition of energy between the electron and the phonon degrees of freedom. Because it's been renormalized, you're going to have some kind of overtone on top of what the actual phonon states are. And so this was motivated by seeing some experimental data, which looked very, very similar, basically, from XYZ. At a workshop last December. And it's a prediction, so this is entirely a theoretical prediction of what you should see if you can measure very, very accurately the state just below the band gap. So your polaron states, of course, in your rigid bands will be just below the band extrema. And when you're fully bound in your polaron state, you have a binding energy of about 23 millielectron volts for the system, then all of the different phonon modes you should see as these oscillations of the order of terahertz frequencies, because there are multiple of what the underlying phonon mode is. And as you go up to the band edge, of course, you're going to a lower and lower binding energy of the polaron state. You're going to an excited polaron state. And so you'd expect those spin coupling constants just to go to zero, and you stop just seeing the oscillation. So finally, just future work. So I should mention Bradley Martin, who just started his PhD with me at Imperial about a week ago now, or a week and a half ago. And there's a lot to do, basically. So these variational polaron theories appear to have been very little worked on since the 1960s. And one of the nice things that we have today, of course, is we have modern computers. So it's a very good opportunity to go back and sort of start adding in a lot of different things, such as making them more material specific, putting ab initio electron phonon matrix elements in, considering multiple phonons, multiple electron bands, and incorporating disorder and excitations. And in the near future, we're actually now starting to look more properly at sort of frequency-dependent mobility, again, with the group of Art and Bakulan, who have a very nice terahertz method of measuring mobilities in these systems. And that's me. So thank you for your attention. I'm afraid I can't actually see or hear anyone, so I hope you're still there, wherever you are. And acknowledgements from funding and people that I've worked with over the years.
Many thanks for your talk, Jarvist. We have some time for a few questions.
Okay, I found you, Cedric, at least. I can see someone.
Yeah. Well, actually, I might just kick off the ball with a very short question. You did mention some very interesting terahertz measurements. I was wondering actually if you would think that ultra-fast spectroscopy, for example, the recent progress in pump probe terahertz spectroscopy, might maybe help disentangle some of the phonon scattering diagrams that you are considering in your theory. Is it something that is ongoing work at the moment? Do people try to describe also non-equilibrium excitations by laser pulse?
I mean, definitely in terms of the level of getting the sort of a frequency dependent mobility. So that's very much been enabled by the sort of modern terahertz approaches. I mean, and this technology is still in its infancy, really, because it's very difficult both to generate terahertz radiation and to measure it. And certainly that means that, once you have frequency dependent mobilities, you can look to different materials and see whether their behavior is truly Judah-like or whether there's additional structure that we need to explain. So yeah, I would absolutely hope that sort of in the near future, we would have some, some definite evidence for materials that are doing unusual scattering, for which would then need to definitely go beyond the sort of semi-classical theories of mobility. Yes, so
so one thing also I just didn't quite understood in details, and maybe other people in the audience were wondering as well. You did allude to the phonon drag and to non-harmonicity, and I think I understood that actually they were kind of captured by the your affective parameters that you have in your theory. What's your claim? Did I understand correctly that your claim is that actually in this polar material, these effects actually are not the dominant one, and essentially you're quite fine by not considering explicitly non-harmonicity? Is that a correct understanding?
The answer is I'm not really sure. So the anharmonicity is almost certainly a problem in terms of the theory. So they assume harmonic modes, and the big reason that you need a harmonic mode is because it's an infinite lifetime, and therefore it can just sit there and exchange energy with your electron state. I don't know to the extent that harmonicity really matters. I guess you have some circumstantial evidence that sort of a model which is based just on harmonic modes predicts the correct mobility in a material which is incredibly anharmonic. So, that's giving you some circumstantial evidence that for whatever reason, it doesn't seem to matter in terms of the mobility theory. But, maybe there was some cancellation of errors of, it pushing in different directions, two different parts of the approximation. So basically my answer is I don't know. It might matter, and certainly this is a very nice test case, these lead halide perovskites, because they're so anharmonic. So hopefully we'll find out.
Thank you for your answer. As anyone else in the audience, is your last chance to ask a question. All right, so if no other question, Jarvist, I'm going to thank you very much for your outstanding contribution. I definitely enjoyed very much your talk. We all did. So thank you again. And again, apologies to everyone for the delay. We are now moving to our last speaker of the day, Eduardo Fertitta, who is senior scientist at Arrival Happy Electron, a company based in London and across in the world. I don't know if actually Eduardo is with us. Yes, perfect. I think you are muted, Eduardo.
Do you hear me now?
Now it's working, yeah.
Sorry about that. So thank you very much, Cedric, once again, and thank you for inviting us and giving us the chance to give a talk, especially after this outstanding, I have to say, line of speaker just before me. So today's my last talk today is going to be a little bit different from the one just before us, because what we're focusing, as Cedric mentioned, we are an R&D company named Happy Electron. And what I'm gonna focus on is mostly showing you some application of most of the methods really we just showed before in the first few talks, especially by Chris and Gabor, in application for industrial applications. So the work I present here is the one of my colleagues, Georg Schusterich and Rakor Sulu and myself. And I should probably give you some context before starting. You probably never heard of this small company called Happy Electron, but you might have heard of our mother company called Arrival, which if you know anything about the EV market in the UK right now, you probably you will have heard that there's been quite some noise lately with some new acquisitions and going public with the release of the future release of buses and commercial vans. So in the big picture of Arrival mission, to really make commercial transport, fully electric, epi electron fits by researching new future energy storage and new future energy production technologies, which go actually both lithium-ion but also beyond lithium-ion. So we are an international team based with some laboratories in London, San Francisco, and St. Petersburg. And we focus a lot of our effort towards research and development, but there is also a lot of effort focused to actually really bring a final product that can actually be integrated into the arrival system. And when I talk with product, I mean not only battery or storage devices, or to be honest, also other sort of devices, but also software technologies that can be integrated into, for instance, the BMS. So epi-electron is quite varied. So we have an experiment, of course, vast experimental skills, but we also have an ever-growing theoretical team. With I mentioned a few of the members right before, and we have a lot of connection clearly with academic partners. And here just to show you a few that we have in the UK and abroad, which really help us to pursue our goal of exploring, as I'm going to say in my next slide, multi-scale modeling of different devices. So in the review of the talk, I'm going to really start by this larger overview of the multi-scale modeling that we are aiming to achieve in the future, and then focus a little bit on some of the simulation work that we carried out at atomic level, and finally review one of the latest work we've been sent for publication very lately. So I will want to avoid to be redundant and repeat all the necessity, as Gabor just said in his talk, all the necessity that there is to try to connect the different scales and all the information you can get by the different scales. But it's certainly true that in industry there is a lot of focus, especially when we talk about battery simulations. There is a lot of focus in what is final element models, or models such as P2D or single particle models to get some access to degradation, which are all basically experimental based, so mostly empirical or semi-empirical, in order to get a model that works and it is cheap, relatively cheap, and it can be integrated in a way into a model of the whole system. This, however, it's definitely not enough. And in the pursuit of trying to connect all the information that you can get, there's a lot of information, of course, that you can get a much smaller scale, and trying to connect this, try to create a model that really is a bottom-up, and it starts from our atomic or nanoscale and goes up all the way to the cell. A lot of effort, as we just mentioned in the former talk, has been done. So far, our interest and our expertise are really into the nano to micro, so I would say, more nano actually. And most of the work we've been doing is really focused on calculating, so predicting crystal stabilities, disordering crystal interface physics, but also some work for ionic diffusion intercollection processes. And now expanding our interest into getting this larger scale to really merge to what Arrival is doing for their systems. It has to be, this was very clear also from what Gabor was said before, it is very clear that there are branches of physics that are really well tailored to tackle one problem. But in order to achieve something like that I would define a holy grail, you really need to define these links, which machine learning is, for instance, one of the methods you can apply, but it's not always clear what is the route to follow. So given this short introduction, I just wanted to really briefly go some of the applications for industrial application we've been interested into lately in our labs. With scale at the atomistic level, we've been focusing mostly, of course, on the study of amorphous materials for electrode application, which is the work that Borja Carosulu has been working on. Of course, the use of interfaces, which I don't need to tell you how key it is, both for battery applications and for different devices, and the study of disorders into cluster, which was a most recent publication. And I'm going to go now into describing the details of these different topics. So the use of amorphous carbons into electrodes, for electrode application is not new. However, at Electron, we've been working to develop some new materials with some new techniques that unfortunately I cannot talk about, based on the agglomeration of nanoclusters. So in order to really model the growth process, we've been using some high throughput air search in order to really get to really get a description of what are the most stable clusters that we can form, exploring different sizes, and then using them as building blocks to describe larger agglomerates that then compose the nanoclusters that the amorphous carbon material we'll be using on. Of course, as size increases, DFT doesn't become anymore an option. So whether for the smaller sizes, most thing was done at the DFT level. Boris put lots of effort into starting to use per potential and performing not only the air searches, but also molecular dynamics, liquid quenching, molecular dynamics compression approaches. As I mentioned before, we have, of course, we work a lot into collaboration with experimentalists. So it's really important for us to get it right, so to say. So for instance, in this graph, we show how by testing over different pseudopotential and ab initio technique, we do compare the sp3 hybridization ratio with respect to sp2 for different nanocluster, the different materials, and which of course DFT is the one that represents the best, but then try to get the most representative potential for potential for the use. Bora can talk more about that maybe during the question session, but the main result is that we generally relied for a long time on the use of EDIP right now, although we have realized that especially as we go to answer more detailed questions, for instance, the formational lithiation layer and lithiation intercalation, the need for new gap potential is starting to get necessary. So this is also work that we're starting to engage with Gabor for. So the work carried out by Georg mostly deals with solid state interfaces. Here I just report I mean, some few example of the situations where interfaces are really crucial in material scientists, of course, ranging from transistors from CPU applications to the production of solid state fuel cell material for solid state fuel cells for oxide transition, batteries, of course, where the number of interfaces is actually really increased to max, and spintronic devices. And the method that, sorry about that, the method that, so in conjunction with the work presented by Chris at the beginning, the method that the Georg applies to do that is really based on using an Ayres randomized search just at the interface while treating the two different regions, the two different grains or two different crystals, basically keeping them fixed. So what we would do in such a case would be basically doing an optimization for the structure optimization for the two different crystals, defining this region with a fixed volume, not creating a random unit cell for that, but randomizing the position of the atom inside the cell, and then performing a geometry optimization and starting again. And doing again, as we saw before, a very large number of time as soon as the global minimum, at least what we think the global minimum is found a decent number of times, let's say. So this is basically the same slide that Chris showed already at the beginning. You know, not surprisingly, because most of this is the work that Georg and has been starting and carried out in the past, and this is simply just to show the number of vast applications that random structure searches for interfaces has been successfully giving in the past. To conclude this presentation, I would just like to discuss one story by itself, which is this work we carried out with a few academic partners. So basically, in this application, so this is a mixed experimental and theoretical work. And the origin of the project was that we were interested in creating some electronic devices based on double perovskite oxide, namely lanthanum titanium iron oxide. Experimental results show that by using PLD, pulse laser deposition, we were able to get very clean and very regular crystals, which, however, didn't present any B-side order, meaning the position of basically the concurrence between crystal structure, for instance, being rock salt and layered or others, that were causing the absence of a clear order that otherwise we would observe in the XRD diffraction pattern. We also saw, interestingly, that although charge transfer between the titanium and iron is observed by XPS, it's only partial, meaning that the iron and titanium, which in a complete charge transfer system would be 4+ and 2+ respectively, from our XPS were only partially oxidized to the 2. The iron was only partially oxidized to the 2+, and mostly still in its 3+ state. Whether the titanium was only present in its 4+ instead of the 2+. Why does it matter? It matters because the interest for this material was to use it as a ferroelectric. And first of all, if there is no clear B-side order, any ferroelectric effect cannot really be taken advantage of. And the same thing goes for the oxidation state, as we cannot have a conserved mechanism that allows us either to change the oxidation state or to change the structure. So we've by applying ab initio method, by applying the DFT plus U and the use of the Ayres approach, we try to understand why this was happening and if we could do anything in the future to change experimental condition to actually tailor our growth through PLD in order to get a more ordered structure with a proper oxidation state. So in order to do that, as I mentioned, we use random sampling, and random sampling has a great advantage in a way above to genealogical algorithms. And this being that really intrinsically yield information about the configurational entropy. This is because in a way your search is, if your search is unbiased, in a way you're really sampling the whole or big chunk of the phase space. And by studying the frequency of occurrence of the minima, you're really able to capture the size of your basin of attraction, which in turn is related to the configurational entropy. Also, by having access in this way to a lot of points scattered all over your spectrum, we were able to use the entropy forming ability formalism in order to calculate in a way to evaluate qualitatively the effect of the entropy at in different regions of the energy spectrum. Moreover, we didn't just focus on the stoichiometric cases, but since we observed experimentally that the oxidation states were not what we thought they were, we argued that the presence of defects might be responsible for that, meaning either extra oxygen or lanthanum vacancies. So we introduced in our search also the presence of such defects, so not just the stoichiometric one. And we couple the spectra obtained for the 3 different stoichiometries to one. What we observed is basically really backs up what we observed experimentally, meaning even, first of all, by looking at the frequency of occurrences, you can notice how there is really a plethora of different minima with different orders, all stable. And moreover, some of those are actually more entropic in the sense that they occur more often than the ground state, meaning, for instance, in this case, the extreme case is the layer 1, which is a frequency of occurrence which is 4 times as high as a ground state. The entropy probability gives are related but different but connected information to what I just said, which is we really see that how we move from the ground state, my entropy increases, and this entropy changes, of course, as the spectrum change. And the spectrum in this case is affected by the fact that by the different chemical potentials of the defects that I'm including as captured by this equation. So what I wanted to do with this was actually to really create a sort of phase diagram at the end, where you can see how the disorder increases as the different chemical potential for the lanthanum from the oxide changes. So I wanted to just stress the EFA is never being used like that. It's generally being used just to evaluate the different entropies between different different alloys and being able to say which one will form more likely than others. But as much as we've seen in literature, it's never been used to actually evaluate the EFA, so the entropy over a spectrum, and not in this fashion with different conditions. But by doing so, you really can capture how at lanthanum poor and oxygen rich, you have basically the increased disorder and how you should really move away from that to decrease it and being and try to really reduce, to optimize your growth conditions. So lots of course from the research and from measurements, basically, if you want virtual measurements all over your spectrum, you can capture much more information than that. We also were interested in looking at the volume distribution, magnetic distribution. Magnetic distribution, clearly for what we said before, that is that our experiments were revealing a titanium which was always oxidized and an iron which was only partially oxidized. And the volume, because clearly the presence of this minima with different stoichiometries, if we want to obtain a crystal which presents vacancies that naturally fits into your crystal, you would likely expect to have unit cell with similar volumes. And I will really start by that. I'll start by that by simply saying that the ones with extra oxygens, at least for the stoichiometries we've seen, they always reveal volume which are much larger than the one of interest, being for the stoichiometry case in the smaller energies. However, the cases with stoichiometry with lanthanum vacancies are much more distributed and present cells that might mix with the stoichiometric one. In this respect, we also observe that no matter what the stoichiometry is, titanium is always 4+, as observed experimentally. However, the presence of the vacancies can actually induce some partial oxidation. We use this observation as a way to basically back up what we were saying and argue that possibly the reason why the disorder is observed and partial oxidation state is observed is actually because we're in a situation with lanthanum defects. This is just to conclude exactly what I just said. So that basically in this just work I just showed you, we started from the experimental results and we started to nicely fit some ab initio observation captured by making an high throughput search over different minima with the use of airs and use those to at least explain why the disorder is formed and what is the role of the defects that can actually be connected to these ratios in observation state, in oxidation state we were seeing. I will just finish here just by thanking you. And so this is, as I mentioned at the beginning, we are for the moment a relatively small theoretical team composed by me, Georg and Bora, dealing with different problems. But I will shamelessly do some advertisements saying that we are expanding and trying to hire more material scientists that can actually help us cover the different problems that we have over device and material simulations. And I think that's my time. Thank you very much.
Thanks a lot, Eduardo, for your nice talk. After a long symposium, we still have some, if there is some energy left for people to ask questions, we still have time. And maybe again, in the meanwhile, while people are gathering and digesting the talk, Eduardo, you mentioned at some point these diagrams where you can tune the partial oxygen and lanthanum pressure.
Mm-hmm.
And there was, as a result, you could actually guide somehow the direction towards this disorder in the bottom left of your diagram. So then the question that might come to mind is, why don't we try to go in the other direction to synthesize a compound with PLD or molecular beam epitaxy? Is there any other limits or challenges to go in this direction in particular?
Not that I'm aware of regarding the oxygen pressure, and I mean this is really how low the oxygen pressure can be in your chamber, which in general is pretty low. And to be honest, I was a little bit surprised of seeing this disorder emerging, because we knew that the oxygen pressure should be in the right realm. And that's also what made us think that the reason why the disorder was emerging wasn't due to the oxygen, but rather to these other axes, but rather to the deformational lanthanum defects. So the experimentalists have actually tried to tune the oxygen pressure, but they didn't improve the results.
Interesting, yeah.
However, this being said, it's also true that even if you, at least from theory, even if you limit yourself into this corner, which means the optimal to have absence of defects, you still have the presence of these higher entropic minima, which are stoichiometric, which means intrinsically, if you try to grow your system this way, literally by growth, and not by a controlled deposition, layer by layer, you're probably really doomed to end up in a situation where you have an intermixing of minima. Yeah.
If no one else is asking questions, I'll just follow up with a more general question. What are the big directions in your view and in the company's view for types of methods that typically are developed within the TYC that could be of use to such a company? You mentioned airs. I was wondering if there are other techniques that might be of relevance or importance.
Oh, airs definitely, especially with Georg now on board, we have the capabilities. And we are now looking into the training of new gap potential for the other project for description of amorphous carbons. And we are expanding into coarse grain simulation to get a little bit higher into larger length scales. Of course, I was mentioning, and also we're ensuring other collaborations with other institutions to also to cover everything that is micro to macro. So really getting into description of finite elements, a bit more this empirical connection. The issue, which is always an open question, is how to connect effectively information coming from a lower length scale to a larger length scale effectively and with yeah, with a machinery that you can then apply to do, in a way, virtual research. And of course, machine learning is one of the ways, as Gabor nicely put in his talk, but they're looking into this.
If there is no other questions, I was thinking to ask Peter, who opened that session with a very general view on how we can describe material using field theory, to maybe comment in your view, Peter, how do you have what in your view is the way forward to model materials, especially in the context of energy, or to screen or find materials for energy?
Yeah, I'm not sure I've got a good answer to that. I mean, it's obviously something which is kind of critical for us. I mean, it was brought up earlier that, you know, it's rarely in the case of an energy material that you have a crystal. Right. So, you know, I mean, if you think about something that I care about a lot, obviously, sort of battery materials, there you really have to be dealing with very complex structures with complicated interfaces, far from stoichiometry, real chemistry happening. And so I think the only way we can really do this is by developing methods that can be used on the kind of scale that Gabor was doing. And I think that for many applications, not all, that is almost the only way forward, because and you can learn from that with things like AIRS. By the way, the talks today were just fabulous, and then I really think we sort of demonstrated how strong a group of researchers that have been pulled together, you know, in the UK and in TYC as well. But I think we need to do that. I think the other side of this is we need to connect better to experiment at the very small scale. And so, you know, this begins to happen, but what a lot is missing is that, you know, you typically don't know what's really in your sample. And so I think, you know, we need a lot better inverse modeling. Again, if I take a battery cathode, in operando, things are happening to it. So, I mean, we can image at the sort of nanoscale and above, but actually we've got very little information about the actual chemistry which is happening, despite the fact that with modern bright X-ray sources, there's enough information that is coming in diffuse scattering that one could really imagine quasi-inverting the diffuse scattering data in terms of a model and bringing them much closer together now, so that we know what is there. And I think that's a very interesting opportunity. And that opportunity is going to get even better as one has more coherence emerging in the synchrotron sources, so that you've actually got much more information that you can get out of a small angle scattering. So I also think, and again, I know this is something that you're doing, that bringing together really detailed understanding of disordered materials studied by all the possible techniques you can, together with the underlying models. You know, and at the same point, I mean, all of the other pieces of the chain need to be there. We must be doing DFT, we must be doing DMFT, so we understand the microscopics. But I think it emerges for energy materials, mostly in this space of, well, you know, I need to be able to treat a million atoms, do it effectively, do it with dynamics, and begin to really incorporate chemistry in that. So that's a personal view. I mean, I don't know whether that's a general or a useful one, but I think we're on the verge of being able to do things which are really quite powerful.
Oh, that's very, 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 very useful, Peter. Thanks a lot. And I think the TYC maybe actually is a right platform to maybe interface maybe with the synchrotrons, the light sources in the UK and abroad, and with experimentalists doing local spectroscopy, and of course involving the larger community of modeling people. As I can see, I'm trying to scroll on my screen to see who among the speakers is still here. I can see that Gabor is still with us, and Jarvist as well. Maybe Gabor, would you like to follow up with your own view as well in terms of how you see the community going forward in the field? I think you are still muted.
One thing that is, I think, is a direct outcome, and I I think it may be that it was a previous conversation with Chris Pickard that led to this, is that these fitting techniques that I talked about, one of the avenues is that they'll be just incorporated into the ab initio codes. So you'll see essentially a timescale improvement of 1,000 if you run a molecular dynamics which is done with an with a fitted force field when it works, and you drop back to DFT when it doesn't. And in fact, if you think about when the first DFT-MD was done on 8 atoms in the early 80s, and now we do, nanosecond dynamics on 100 atoms, most of that improvement is not Moore's law. That's Mike Payne's point. Most of that is algorithms. Some of it is Moore's law, but not most of it. And the next factor of 1,000 will not come from Moore's law. It will come from an interpolation scheme like this. And that's definitely one way. And there are already papers that are doing that.
So no, indeed. So the progress made by algorithm is actually definitely enabling us to look at, as you said in your talk, not being scared of the amount of data that we have. We have now the capability to process a tremendous amount of data and indeed accelerate simulation using interpolation. I think that joins also Peter's point, if I may, because somehow we have to interface the DFT community and the MD community and the machine learning community to make this kind of progress, if I understand you correctly, Gabor, as well. It is somehow a very cross-disciplinary effort.
But there are But then let's look at the quantum chemistry side, where you have an exponential scaling. And this is where, work of people like George Booth, who were thinking of correlated quantum chemistry with its exponential scaling. And how can that be tamed with the appropriate, it's the wrong basis, because you need an exponential number of parameters, determinants to get decent accuracy. But that, it doesn't feel right. I think we could try and get a better basis, a better interpolation of the wave functions now, not the potential energy surface. So I think this idea is actually much more general than just potential energy surfaces. It's about finding the right descriptors, finding the right basis functions numerically.
I see.
And I think that will have a much wider impact, including wave function methods.
I see. I will now maybe turn to Jarvist, because we didn't discuss much phonon in all that process. I mean, we did discuss ionic motion and optimization, but you introduced something new in the series of talk today, which was how can we actually connect now and describe particles which are higher order, such as polaron, for example. So what would be your view, Jarvist, on the future of modeling techniques for energy problems?
I think I agree with all the previous speakers that, we're going to end up needing to bridge a lot of different areas, so both experiment and theory, to really understand what's going on, and also actually sort of combine approaches from lots of different codes. What I have absolutely no idea, though, is how we're going to do it, because I mean, the problem is you actually need people with expertise in all of these different areas, and you need to be able to make codes that are compatible and can talk to each other. And that is a big ask, particularly when we're actually just sort of independent academic groups working in our own areas. So, I guess I don't have anything to add in terms of what we need to do. Just leave this question of like, I don't know what it's going to look like over the next, 30, 40 years in terms of how we're going to do it.
It's definitely a challenge and an interesting direction for the overall community. So maybe the solution, Peter and Arash, will be to merge the Faraday Foundation and TYC, maybe as a halfway joke. But no, indeed, interfacing larger groups.
Well, I mean, I'll comment actually that I'm not sure about that, but I think the UK needs a national energy lab. Right? That's a sort of a glaring miss, actually, to be able to exploit on a sort of a more industrial scale some of the things that you're doing to bring these things together. So it's, I'm always stunned by how well the computational community has done in the UK, despite the headwinds. If there was a little more coherent support, I think it would work better.
I think it's a perfect opportunity for me to give the last final word to Arash Mostofi, who is director, one of the directors of the TYC. And Arash, would you like to say maybe a few words to conclude this symposium, if you are still with us? And if Arash is not with us right now, I'm checking if Johan maybe is here. I think we'll have to pass on that last chance for the TYC to officially make a statement. So in that case, would anyone...
Hi, that's still me as a director.
Oh, sorry, Carla, I didn't see you by all means. Would you like to comment on the final last one?
Thank you very much for this very interesting and exciting symposium. Yes, I think it's been very inspiring and very interesting. And yes, so it's good to hear all these ideas and development, and we hope that the TYC can interface and give a contribution to this as well. So just to be very brief, on behalf of all the other co-directors.
Thank you, Carla. So in that case, I mean, this concludes our first TYC symposium. I hope that you did enjoy, if not all of it, parts of it, and we definitely enjoyed contributing to this organization. So thank you all, and we'll be in touch with further TYC events. And thanks again, a big thank to all the speakers, Peter, Gabor, Jarvist, and Chris, who left us already. So a big applause to all of you. And yes, we'll tune in soon. Bye, everyone, then. Bye.